I hope you feel well and you still have some power to pay attention to me today. Now, as Mikhail said, my name is Gergely Takács. I'm from the same university as this, the Slovak University of Technology, but from the Faculty of Mechanical Engineering and from the Department of, Institute of Automation, Measurement and Applied Informatics. Now, today we're going to look at hardware implementation of control algorithms and MPC on the Arduino platform. Now, my first question is, I don't know many of you personally, so my first question is, let me know which one of you has programmed microcontrollers, not necessarily Arduinos, any microcontrollers before. Okay? So there is a big, okay. So that's good. Anyways, if you think that I'm going too slowly, too fast, stop me or just tell me that we already know this is boring. Just go ahead and tell us other things. Okay, so we know generic microcontrollers. Which one of you has used Arduinos before? Okay, so that's a bit different. Okay, that's fine. Now, let's go forward. I have a couple of lovely helpers today. First of them is Martin Kalus over there. He's the creator and designer of the Flexi device. Then we have Gabriel Batista somewhere there hiding in the dark, in the twilight zone. So that's Gabriel. We have Eric Mikuláš next to Gabriel. Okay. And we have Gabor Penzinger. So these guys will help me today. If you get stuck, if you have an error message, if something doesn't really work, then do not hesitate. Let them know, and they will try to help you as best as they can. Now, you can connect to me at any time, even after the workshop. Feel free to write me an email. I have an outdated web page, which I haven't really worked out for 7 years, so that's really useful. And you can connect to me at any possible way you can. No, I don't have a Tinder. I'm taken. Sorry. Anyways, before I start with the material, there's time for some very early and premature self-promotion. All of the material I'm going to talk to you about today, how to use the Arduino in control engineering, will be a part of a book I'm working on. It's really early to release that. However, if anyone is interested, I'm happy to provide you with a really early draft. Of course, if you try to correct me and give me some hints. So that's not a problem. Write me an email and I can hook you up with a copy. This is still years ahead. I'm just telling you that it's happening. Now, let's talk about some organizational things. Now, you know the Tempo summer workshop webpage very well, and there you can find the Arduino section. Which one of you has already installed the IDE, the Arduino IDE? Okay, so most. If not, please go on to Arduino CC, the webpage Arduino CC, and download and install the software. The installation is really simple, just 4 clicks. I will talk about that, but there is nothing really complicated about that. Now, besides this presentation, you can find this presentation to follow along on your very own computer. You have 2 types of files and 2 sets of files. One of them has the word exercise attached to it, and by exercise I mean that you should use these during today's lectures and exercises. Now there is another set of files. This is called Tempo 2017 zip, and this contains the full files. Okay, this is the full solution. Use this if you need to consult how to do things. Use this if you are stuck, or use this to help yourself out. Now, these files contain 2 libraries. They are both freely available. You can also download them off the internet, but they are included. These 2 software libraries are the following. One of them is for the Flexi device. We will be talking about this in detail. This thing, it just helps you to access its inputs and outputs from the Arduino, from the microcontroller. So that's basically just an I/O library. The other one is called Timer1. Again, it's a freely available library. The Timer1 library is meant to simplify your life when you are trying to do sampling and discrete sampling on hardware, the Arduino hardware. Now, all the exercises are separated by folders. You should be able to recognize which one you need and do not need. The files for the Arduino IDE are called, or with the, have the extension .ino, and they have to be in their very own folder. Okay, so you cannot have an Arduino IDE file outside a folder which is named the same. So that's why the structure looks as it does right now. Now, what I mean by the exercise and full files, the exercise files will look something like this. You just have comments. You have a couple of parts already written in there, so you don't have to type along. And the rest you have to fill in yourself. Again, if you get stuck, you have the full listing in the other zip file. So please do download these, extract these on your computer so you can access these files. Now, tomorrow you will have the project day. And for this project, I have already listed some ideas, again, on the Tempo website. There are currently about 12 pages. These are meant to be group projects for 2 or at most, I guess, 3 people. So you can already look at these and maybe select one that you like. All right, so let's go to the first part. And as many of you have used microcontrollers before, maybe I'll try to speed this up a little bit, but let me know if you can follow along. Now, in the first part, let's talk about Arduinos and microcontrollers. Now, the whole Tempo project, which is basically the excuse to organize this workshop, is a training in embedded predictive control and optimization. But where is the embedded part? I mean, so far, many of you, especially from the Tempo workshop, have used full-size computers. You've done simulations. Maybe you've done even real-time experiments on large-scale computers, or maybe you use PLCs. But I would say I'm missing the little chip in there. I'm missing it from the Tempo workshop. So today we're going to fill that little gap, and we're going to do embedded predictive control on a real microcontroller, not a PLC and not a PC. Now, all of you know your computers. All of you know how your computer works. It has a processor. It has a volatile memory and a non-volatile memory. The volatile memory, as the name suggests, it's just gone. If you turn the computer off, if there is no power, the volatile memory just disappears. But for that, you get a bit of speed. So the volatile memory, or random access memory in your computer, is faster, but it doesn't really remember what you're doing. Now you also have non-volatile memory, which if you turn off your computer, stays around. This memory is a bit slower, but larger. You also have your processor and all sorts of peripherals, ranging from your mouse to your keyboard and your monitor. Now these parts, even if they are located on the same circuit board, they are separate. However, in a microcontroller, they are all located within the same single chip. So one thing to realize is you have your various kinds of memories. You have your peripherals and you have your microcontroller in one single chip. That's all you have. That's your computer. That's what you have to work with, and that's what you have to program. Now, of course, there are different classes of systems on a chip or microcontrollers. And the first group I would like to briefly introduce, I wouldn't maybe even call a microcontroller. Now, these are very common. These chips are called ARM Cortex-A. Several manufacturers make them. ARM is the company which designed the chip, and they license it out to other companies to make. And Cortex-A, the A means application. What does application mean? These microcontrollers, I wouldn't even call them microcontrollers, systems on a chip, are typical for use in mobile phones and fairly high performance applications. So what you would find in a mobile phone, maybe an older one, is roughly what an ARM Cortex-A microchip is. Now, of course, you can buy these things and you can buy prototyping boards for these chips. One of the most well-known is the Raspberry Pi device. Now, the Raspberry Pi and other similar devices, they're a bit different than classical microcontrollers. One big reason is that they do not have non-volatile memory inside the chip. Okay, so the Cortex-A series, these chips, need another microchip which stores your program, your operating system, whatever. Now, the Cortex-A chips usually do not have a specific software meant for the given application. Instead, they have generic operating systems. What does this mean? You can use Android or Linux and run them on the Raspberry Pi and our ARM Cortex-A processors. These are not the processors you can typically find in consumer applications like washing machines or drills, power drills, and things like that. These are more powerful. You need displays, you will have an operating system, and all of that. Now, another class of microcontrollers I'm mentioning today is again designed by the firm ARM, and these are denoted by the letter M. And the M here means microcontroller. So these are the true microcontrollers. These are the ones we are going to be dealing with today. And these devices do not have an operating system. There is nothing on them. Everything has to be written by you. Every piece of software, every piece of driver, everything needs to be written by you. There is a volatile memory, so it has RAM. There is a non-volatile memory where you can store your program. That's the analogy of your hard drive in your computer. So there is inside, and there is, of course, a microprocessor, a processor inside. Microcontrollers also have various peripheral units. So what are your peripherals on your computer? For example, the keyboard. But think about it, the keyboard is just a bunch of buttons. It's just a bunch of switches. So of course, a microcontroller can sense switches, or you can send digital signals to it. But there are also other types of peripherals like buses, digital buses to communicate with sensors and actuators. There are peripherals which you don't even see. They are inside, called timers and counters, which help you to count events or time events or create a sampling framework. Now, of course, these devices, you don't really have to take a chip like this and play around with it. Of course, they do have similar boards as the Arduino. So you can buy, for example, something like this. This is very similar to the Arduino. This is made by ST Microelectronics, a French company currently. They also license the ARM Cortex system from them. And you can hook this up to the computer similarly to the Arduino and start to program it. One difficulty is that ARM Cortex-M chips are a lot more complex than the one microchip located in your Arduino. They're a lot more complex to program. For example, just to blink an LED, you will need dozens of lines of code which will specify how fast your microprocessor is, etc., etc. So it can be really frustrating to start with this. What you get for it, however, is increased memory space and increased speed. Just to have an idea, some of these devices can go up to 400 megahertz in speed, while still being a microcontroller and while still costing a couple of euros or dollars, whatever. So they are fairly cheap, I mean the microcontroller itself. The second problem, if you're starting to learn programming microcontrollers on these boards, is that the ecosystem around it, the tutorials, the web pages dedicated to it are not that clear. So it's a bit harder to begin with these things. But of course, very rewarding as mainly because of their speed and power. So I would recommend if you want to use these guys, then first learn to use something simpler like the Arduino or 8-bit microcontrollers, and then move on to these. I have lots of demonstration devices around, so I'm going to be passing these around with the hope that it eventually returns to me. Okay, just feel free to take it out of the box, look at it, okay, pass it around. Okay, so these are the ARM Cortex-M series microcontrollers. Now, there is one question of if you have a chip like this, okay? If you have a chip like this, or if you have a microcontroller like this, it doesn't really matter, it's just a package. But how do you get your program on it? Okay, there is no USB port, there is no Bluetooth. How do you program these things? Now, normally, what you need to program these microcontrollers are programmers. Now, programmers are hardware devices, such as the ones on the screen. You have to find certain leads of the microcontroller, connect the programmer to it, and then interface the programmer to your computer, and then you can download your program to the chip and run it on the chip. So normally, to program microcontrollers, you will need a programmer. Now, programmers can take many shapes and sizes. I have taken Atmel Ice with me for you to show just for demonstration purposes. This is this guy. It's a very powerful device. It not only lets you to download your code to the chip, but it can also help you to run through your code step by step. So you see your C code, and then you do step-by-step debugging with this little powerful tool. Not so expensive, they are around 100 euros. So by this, you can buy a chip and go on programming yourself, okay? Feel free to open it, have a look at it. These are the programmers. Now, the microcontrollers themselves come in different packages. Now, the package you have on your Arduino, on the Arduino Unos you will be using today, is this one. Okay, it looks like this, the chip looks like this. It's called the double inline package. Why is it so popular? In the Arduino, the original Arduino, they chose to use a microcontroller which had this double inline package. And with a double inline package, even hobbyists, even you, can take it and solder the leads to a PCB. You can actually work with it. It's not too small. So that was the reason. But of course, the majority of microcontrollers in modern devices come in surface mount packages, and it would be really, really hard to solder the leads on this. But it's the same idea. So even the microcontroller in the Arduino has a version which is double inline package, so you can work with it easily as a hobbyist, and also a surface mount package. And this is actually what I'm talking about. So the seemingly large chip is what you have in your Arduino Uno, but as a hobbyist, that's very good that it's large because you can work with it. But it has also a very small version. You can mount it inside miniature devices. If it's a power drill, if it's a child's toy, if it's a medical device, it doesn't matter. It fits inside because it's very small. Now, so the Arduino. Why do we even need the Arduino, and why aren't we programming chips? Before I go into that, here's another demo case. Feel free to pass it around and open it. There are lots of chips. You have some writing on it so you can figure out what it is. These are different microchips inside, and there are some mostly non-functioning Chinese programmers too. I do not really recommend to buy these off eBay because they mostly don't work. So you can pass this around while I speak. Now, the Arduino. The Arduino idea is that it's a prototyping board, just like the ones I've passed around. Now, this is a different one that you have in the Flexi, but let's look at it, what it contains. Well, first of all, it contains a microcontroller. And the microcontroller's leads can be accessed through these header pins. So there's nothing else in there, just accessing, making you easier to access the pins of the microcontroller. Now, at this time, I think, Martin, it would be really nice if they actually had the Arduinos. So can you please distribute, and then you can inspect your hardware. Okay, while Martin is distributing the Arduinos, I'll continue to speak. So that's one thing, basically, one of the ideas behind the Arduino and similar boards is to let you access the pins of the microcontroller. The second role of the next role of the microcontroller is that it bypasses the need of a programmer. So for this guy, you do not really need to buy an external programmer like that. You do not really need to connect anything to the microprocessor because everything is built in on this board. You only connect it to your computer and no need for a programmer. Now, Arduino does this by a very clever trick. I'm not going to go into any details, but if you notice, there is a second microcontroller in both Arduinos. So there is a second microcontroller, E here, on both Arduinos, and that second microcontroller actually makes it possible for you to connect it via USB to your computer. Now, there are other little features. Okay, so we have access to the pins. We have programming capability. And there is power. So these boards can be powered two ways. Either you can hook it up to your USB port and it is powered already. You don't need a power source. Or some people do a project. They do whatever they want. And they connect to this barrel jack two batteries. Okay, so you can run your Arduino off batteries. It chooses it automatically. Okay, so this is basically the power circuitry in your Arduino. This is a voltage regulator, some capacitors. This is the power circuitry. As every computer, the most important feature is the reset button. Okay, so every one of these boards has a reset button. Arduinos. Let's see what else. Now, I've told you that you can program your Arduinos via USB, but you can also connect a programmer, what we said, the hardware, to it directly. So there are some pins, these pins called ICSP pins, in-circuit system programmer pins, and you can connect a programmer directly to the chip. That's the same thing as you would just take a chip from the kit and try to play along with it. Okay, so you can also program your chip externally. Now we have at least three LEDs, actually four LEDs in your Arduino. One of them is just an on LED. The on LED just says that it's under power. It says nothing else about it. Okay, on, and that's it. Wow, that's not good. That's okay.
Is that yours?
Yeah, it was mine. Okay, we'll ask Martin to solve this situation. Okay, the other LEDs, you have an LED marked with an L. Okay, just a simple L. This LED is up to you. The LED is really up to you. It's connected to one of the physical pins of the device, and you can use it to signal whatever you want. So this is the most basic test you can do on an Arduino. It's inside the Flexi. The same thing, it's a different Arduino though. So you can use that to your advantage. Now there are two more LEDs, TX as transmit and RX as receive. TX and RX signify the communication between your computer and the chip. So if there is communication between your computer and chip going on, then these LEDs will start to flash rapidly. Now, the last component is very important. This is the oblong, elliptic piece of hardware. Right on it, you have on the Uno 2. This is a crystal. This is a crystal oscillator. And this determines the speed of the execution. Based on the oscillations of this crystal, the Arduino will start its programmed start to step in the instructions. Now, The crystal, if you can see it inside your Flexi, has 16 written on it. And 16 means that 16 megahertz is the speed by which the processor inside the microcontroller will step forward your program. 16 megahertz is not too fast, but these things are meant to be built in, or in other words, embedded in applications and do just a single task and do not run an email program and Office and other things. So 16 megahertz is actually not that bad. Now the AVR microcontrollers. These microcontrollers belong to a family. So no matter that you use an Arduino Uno with a processor made by the company Atmel, it's an Atmel Atmega 328, this microcontroller belongs to a family of microcontrollers designated with the name AVR. Nobody actually knows what AVR means. This is a running joke in the engineering community. Anyways, so if you learn to program the Arduino Uno, there is not an issue to switch to other boards. It's the same thing. It's the same idea. This just has more memory, more pins, and that's all. So if you learn one, you can use the other one as well. Now let's look at the construction of the chip in the Arduino Uno and the AVR. So let's say the gray area is your microcontroller. Of course, it has a microprocessor. Now, how does the microprocessor want to go forward? How does the microprocessor know when to advance one step forward in your program? This is based on the crystal oscillator, which is basically governing how the microprocessor fetches instructions. Now, where are the programs stored? The programs are stored in the non-volatile memory, which is in this case called read-only memory. Is your hard drive in your computer read-only memory? No, it's not. You can write to your hard drive. But here is an important distinction. In this microcontroller and in most microcontrollers, you can't just write on the hard drive during the execution of the program. You can create your own programs, but your program itself cannot really write on this part. Where it can write and where it can use the operations is the RAM. The random access memory, the volatile random access memory, which is much smaller than the program memory. And it's also, of course, volatile, but it's a bit faster. Now, the RAM in your Arduino is 2 kilobytes. Okay, that's all you have. And the flash in your Arduino, we call it flash or ROM, that's the same thing. So the part to store your programs is 32 kilobytes. That's all you have, and believe me, 32 kilobytes is a plenty if you have to write your software from the ground up. If you start with nothing and you are writing your program in C and then compiling it into machine code, 32 kilobytes can be plenty. Now in microcontrollers, there's a third type of memory. This type of memory you don't have in your computer. It's called the EEPROM. It's an electronically erasable programmable ROM. And what is the idea? If you have a program that wants to store something while it's running, it can't store it in the ROM. It's read-only. If it's running and you want to be able to remember that variable after a restart, then you can't really store it in the random access memory because it's volatile. If you reset your system, if you turn off your system, it's gone, poof. So there is a third type of memory, and this third type of memory allows you to write from your program. However, it remembers it. Now there is 1 kilobyte of this special type of memory in your Arduino Uno. And of course, all the peripherals you have in your microcontroller are built in essentially to the microcontroller. So you have digital inputs, digital outputs, all sort of buses that you can use to connect sensors, advanced sensors like dust detectors and accelerometers and whatever. And of course, there are some peripherals we are going to touch later, which are built in and do not really have lead outside, and these are the timers and counters and interrupt system. I'm going to touch these later. Now, the architecture of the processor in the Arduino is 8 bits. What does this mean? The basic unit it uses to store data is 8 pieces of zeros and ones. One instruction is 8 pieces of zeros and ones. Does that mean that the largest number it can operate with is 255? No, it does not. It just means that it has to do some clever trickery to do mathematics and operations above this number. But the base unit of the architecture is just 8 bits. Now the processors or the boards I have let to circulate, which say ARM Cortex-M, are 32-bit processors. They have larger memory addressing spaces, and also their instructions, a single instruction, processor instruction, can be a lot more complex. Now, in the introduction, it is very important, if you don't know the Arduinos, it is important to mention that it is very easy to expand the functionality of your Arduino without any, let's say, manual work and connecting any microprocessors. You have something which is called a shield. They call it shield. Now, shields are just modules you can put on top of your Arduino, just insert to get advanced functionality. For example, the Arduino, the company itself, makes the Ethernet shield. Yes, this little processor with 2 kilobytes of memory can connect to the internet. So you can connect to the Ethernet and you don't have to manually solder all sorts of parts. You can just take the shield and experiment with it. Or for example, if you want to connect a motor to your Arduino, then there is the motor shield. Now this whole ecosystem of Arduinos is open. That means that other companies are very welcome to create their own shields and accessories to the Arduino. And some of these are shown in this slide. They are so-called prototyping shields for you to mess around with the soldering iron. There is a shield called a data logging shield, which has an SD card. Of course, the Arduino can write on an SD card for long-time data logging, things like that. You can connect it to XB. There are very precise analog outputs and inputs. So there are millions of types of hardware that can be used with your Arduino. Okay, so let's do some work finally. So if you haven't installed the Arduino IDE, please do it now. In the Windows operating system, this is really easy. All you go through is just these 4 little windows. It just asks you to agree to the terms. Then you select the components. I would say select everything. The Arduino IDE is about 100 megabytes, so it's not very large. You select your folder, and then the installation goes on. So it's nothing too complicated. However, if you use a Linux operating system, anyone with a Linux using right now? Okay. I wouldn't recommend to download it to automatic systems. I would recommend you to download it off their website, because in the Linux repositories, they have a very old version. Okay? So download the file, install their file, extract, uncompress, install it, and then, of course, you can open a terminal and just type /install sh to the terminal, and then you can launch it by the icon. Again, the installation is not very complicated in Linux either. Mac, anyone using a Mac with the IDE? Okay, 1 guy, 2 guy, 3 people, okay. So in the Mac, do you already have the IDE? Yes. Okay, so was it installing very hard? Not really, right? Okay, so you download it, extract it, launch it, nothing very interesting going on. Now, I would like you to open the IDE and get yourselves acquainted with the IDE. So this is the programming environment you're going to be using today. It's called the Arduino IDE, Integrated Development Environment. Here you see the name of your program. Now it says sketch. What is sketch? Sketch is a drawing. Sketch is essentially a pre-drawing. It's like a prototype drawing. And why do they call the programs drawings? Because Arduino, the original one, was meant to be used by artists and designers and creative people. So that's why they named it sketch. So sketch just means your Arduino program. Now you have a couple of buttons over here. And let's start with the check mark. The check mark, if you click the check mark, it will compile your program. It will turn it into machine code that the Arduino, the chip on the Arduino understands, but it will not upload it to the device. Okay, it's just a check. It can confirm whether your syntax is okay or not. The next one, the arrow pointing to the right, pointing to the right, that's your deployment button. So if you've written your little program, you click on this, then it will compile your program. It will turn it into code that is understood by the little chip inside. And it will also send it to the chip. Okay? So this is full deployment. This is just new file, open and close, so there is nothing really interesting going on here. The white area is, of course, where your program goes. That's not too surprising. And the black area is whatever messages the compilers and downloaders give you. So if you have errors or if you don't have errors, it will appear in this black area. Now, at the bottom, I'm not sure what you see, but for me it says Arduino Genuino Mega on COM13. So this is really vital information, because before you start to download your program onto your Arduino, the IDE has to know two things. What sort of chip you have inside. Okay, so you have to tell if you have an Arduino Uno, like you have in your Flexis, or for example, this one, an Arduino Mega. Okay, so you can change this in the tools menu, but you have to always tell in advance which type of microcontroller you want to deploy your code on. And COM13 on Windows, it says something different on Apple computers, Linux computers, is the address of the virtual communication port to your Arduino. Now the way it connects, your computer connects to the Arduino is through USB. However, your computer will think this is a serial port. So that's why the Windows computers name it as a virtual serial port. It's a serial communication, and you have to check which virtual serial port you are actually using at the moment. Now, I forgot to tell you something. Of course, there are different Arduinos. Arduino Uno is probably the most basic one, the most well-known one, the one you have. But you have this one. This is the Arduino Mega. I've been holding in my hand for the past 15 minutes. Same idea, just more inputs and outputs and bigger memory, but the same speed. Okay, and there's, for example, this one. This is an Arduino too. It's an Arduino board. It's a lot smaller, so you can do your own project, build into something, and it still works. Okay, a really small one. And surprisingly, on Monday you had PLCs, right? What is this? This is a PLC. Guess what's inside? It's a full Arduino. If you take this apart, there's an Arduino inside. However, it has modules to communicate with the outside world, digital, analog, etc. And this thing actually has more expensive versions with Ethernet and all sort of industrial communication systems. But inside, there's still an Arduino. Okay, so just feel free to pass this around, inspect this, pass it around, please. Okay, now the last thing I want to show in the Arduino IDE is the little magnifying glass in the corner. You see this magnifying glass? The magnifying glass is for spying on something, and this time it is for spying on the communication between your computer and the Arduino. your Arduino can talk back to your computer, and if you want to see what the Arduino has to say, then you can click on this little icon and it opens a console, a serial console. Now, let's begin the work. So in the Arduino world, what is the programming language? Some people say that you're programming in an Arduino programming language. Bullshit. It's C. The Arduino programming language is just a dialect of C. The Arduino IDE just uses a couple shortcuts to make your life easier. However, this is still C or C++. So if you know C, you know Arduino. And if you learn Arduino, you will know C. Now in the Arduino world, there are two functions, C functions, that have to be a part of your project. One is setup. And everything you put in the setup code runs only once. Runs only once after you power on your device or after you reset your device. So there are two. If you push the reset button, it will start again and booting up. So this is, if you want, your boot up sequence, okay? And loop. Well, loop just goes round and round and round and round. You put there everything which needs to be checked repeatedly, okay? This is just a big loop. And of course, there is nothing else on your chip. Your chip is empty. So you start from here. There is no operating system. There is nothing. Just these two programs. Now, every one of your Arduino projects needs these two pieces of programs, a setup and a loop. Setup, again, runs one, loop runs round and round. Now, your first job will be to hook up your Arduino to your computer. Okay, so that's the first job we are going to do today. Okay. Now, for those of you who have worked with microcontrollers, might be wondering, where are the definition files? How does the compiler know what is 13 or what is digital write? Of course, the maybe overly simplified world of the Arduino IDE under the hood is quite complicated. So what happens in reality is something like this. You have your source code, your .ini file, and the Arduino IDE will do additional changes. This means that even though your text file, your .ini file, doesn't start with including header files and things like that, the first thing what the Arduino IDE does is just pastes in the beginning of that file. Now, then you should have a C source file which could be compiled by a proper regular compiler, because the Arduino IDE will look up instances of your programs which are of course non-standard for C, such as digital write, delay, things like that, and it will replace in your code. Then this is compiled using an open source compiler called AVR GCC to object codes. It is linked, several objects are linked, and a machine code is generated from that. Now it's important to realize, when you click in your Arduino IDE, when you click on which board you are using, this is when you're telling the Arduino IDE that you should compile it for this specific processor. What you're compiling from your C code is for a specific type of microprocessor, a microcontroller. Now after that, there is a little file format change. It is changed to an Intel hex file, and there is a software called AVR downloader and uploader. Weirdly, it says AVR dude. Okay, so this one helps you to upload your program into the chip. And the program, what you just wrote, the blinking LED, is then already located here inside the chip. Okay, there is some intricate trickery of how the upload is done. For those of you who are used to working with programmers, I'm just telling you, don't need to understand this, but it uses a bootloader, and it looks if something is going on in the serial link. So that's how it uploads to the microchip. Now, so what is behind all these functions, and why did I say that Arduino, the programming language, is essentially C? Because when you write digital write D13 high, what happens is that the Arduino IDE looks up what digital write is, and of course that's just a regular old C function, it's nothing else. The Arduino IDE, it's just designed to simplify things, and it lets you concentrate on the application and not on the details on turning things on and off and using buses. Okay. Now, yes?
Is there an easy way to access the C code that is generated? Or
that is generated?
Or, yeah, like I guess they first package all the C code together and then they compile it. Is that, can you find it?
I've never really felt the need. You probably can. So it probably, the C code which is compiled from the, let's say, Arduino wrapper is surely stored somewhere. I never really felt the need to inspect it. Okay? So, for those of you who have not worked with microcontrollers, you might be wondering, how do we turn on the LED? Now, when I said that there are 3 types of memories, that's not completely true. There is a 4th one. It's essentially a memory location, which is called a register. Now, a register is a special type of memory location that you can read and write. And this memory location controls the hardware. So, for example, if you want to output a voltage on a pin, then you have to find which special memory location called a register is this pin belonging to. For example, in the Arduino Uno, the pins, the physical pins, the leads, are divided into banks of 8 because we have an 8-bit processor, so there are banks of 8. These banks are divided by, or denoted by letters A, B, C. Now, the 13 is located in port B, and if I just write port B is a binary number of 001000, then I'm turning on the pin. That's what's happening in the background. There are memory locations I'm writing to, and if that memory location is on, then it basically physically, imagine as if physically connecting 2 wires and outputting the voltage on the pin of the microcontroller. Now, let's go a little bit further, and let's talk about how the Arduino can talk back to you. And this is a very powerful and important feature. It is done using serial communication. So what is serial communication? What's the difference between serial and parallel? Very easy. Of course, in a serial communication, you have one information channel, and your information, your bits of code are flowing to the channel one by one in sequence. In a parallel communication system, you have several wires or several information channels, and your information is flowing parallel in these channels. So what are the advantages and disadvantages? Of course, parallel communication is a lot faster. That's obvious. But, of course, you need more wires or more channels. Now, the Arduino doesn't have any sort of way to do parallel communication, but it has a serial channel. And the serial channel is connected to your computer. Now, if you look at your Arduino, find pins 0 and 1. If you can see 0 and 1. It has a writing on it. It says TX and RX. TX and RX stands for transmit and receive. Now, the Arduino Uno uses this one serial channel to do everything. It uses to upload your program to the microcontroller, and it also uses this channel to communicate with your computer. Now, different chips might have more of these, and for example, the Arduino Mega, which is lost somewhere there, has 4 of these, 4 pairs of serial ports, RX, pairs of RX and TX. Now the idea how to connect, these are just wires. How to connect two devices with serial communication is you cross these wires. So the transmission of one goes into the receiver of the other. The transmit of the other goes into the receiver of the first one. And of course, it is important to note from the standpoint of electronics that you also have a common ground lead. So you need for communication both ways with two devices using the serial port, you need 3 pieces of wires, and that's it. If you want to do only one way of communication, just to send something, just to receive something, that's fine. You just ditch the other channel, and you have 2 wires. You have 1 wire connected to the other device. You just connect it to this pin, and that's all. And then the ground pin, which is the 0 volts reference on your device. Now, these serial communication links have some sort of agreed upon form. And this is roughly how it looks like. If the line is idling, the line is high. So you have a logical high value. Now, there must be some sort of agreement between the receiver and transmitter on what sort of speed we are using. Okay, so there is no clock signal. We have to agree in advance what sort of speed we are using. But if we know the speed, then we can divide information into these little windows, and then we can detect if we have a 0, if we have a 1. So if we agree on the speed, then we can start the communication with a start bit and then transmit the data. We can even have a very primitive way of detecting if the information transmitted is correct. It is called parity. It's the parity bit. And then you usually have a stop bit. So this is the frame of communication. You don't need to analyze this when you're working with the Arduino. I'm just saying what's happening in the wires if you connect it to another Arduino or to a computer. So for example, if you transmit Arduino, then you have a digital and information going on in your wires, up and down, off and on, off and on, off and on. And as long as you agree on the speed of the communication, then you can decode this little information. Now, the speed, the pause, ignore the pause, that's just my error. The speed of the communication is not given in letters. It's not even given in bits. They call it bauds or baud rate. Why? Because you also have the starting and stopping and other types of communication parts of the frame. So they are standard baud rates and non-standard baud rates. If in doubt, you can use 9600. That's 9600 ons and offs for a second. Of course, that doesn't mean that you have 9600 letters or pieces of characters or numbers or whatever. It's just the digital ons and offs. And this type of communication, as I said, doesn't really have a clock signal. So you need to agree in advance what sort of speed you're using. And if you're using your Arduino, the serial port, that's the first thing you do. You say what sort of speed are we using. So the first thing you do is you say serial dot begin 9600, that's the speed, whatever speed you choose. And you put this in the setup part of your code. So you need to tell once what is the speed you should communicate with. Yes?
From the point of view of C language, what is serial?
I'm sorry?
From the point of view of...
Serial is not a standard C language function. Arduino IDE will look up the equivalent of serial.
I mean, it's not C, it's C++.
It's C++ actually.
And serial is an object, so you have first create.
So does it mean that I can program like in C++?
Yes, yes, yes. You can use C or C++ in the Arduino IDE, and actually most of the functions of the Arduino IDE, or all of the functions, are programmed in C++.
Serial is a global object.
Serial is a global object. Serial is part of the Arduino dialect, so you can access it anytime.
And what is backslash?
That's my error, which I made in LaTeX. That's nothing. Ignore that. Okay, the backslash pause, that's nothing. Okay, ignore that. That's just my mistake in the LaTeX code. It should pause before I continue. But anyways, okay. So serial.begin is how you initiate serial communication. Now, if you want to print a text, an arbitrary text, any string goes in quotation marks, and you can print it serial.print. What will happen if you do this? What will happen if you print serial.print? Well, your Arduino will send this text, my text, over this line, physically. Ons and offs, ons and offs. And if you have a way to decode it, like your computer or another Arduino, then you can read it. Okay? Now, it is important to note that printing my text in one line is the same as printing it like this. Okay? If you don't end the line, then it will be the same. If you divide parts of your text to several lines, that's completely fine. And that comes in very handy if you combine this with printing variables. So if you say serial print, and this is a variable which is changing, then it will just print that variable. So if you have any sort of number, like a state or reference or whatever, you want to output on your serial link, you just say my variable, the name of your variable, and it will print to the serial. Now, this is the most important part, and these are just some additional tricks. Okay? If you write comma and a number next to it, it will specify how many decimal points you want to print. You can also specify what sort of numeric representation you want. So you can say binary, decimal, hexadecimal, etc. If you do a comma next to your variable, and then the designation of that numeric format. Now, one more important thing to remember: if you don't say serial.print, but serial.print lana as line, that puts a line ending, as if you would press enter. Press enter at the end of your line. Okay, that's it. That's it, how you can use the serial link on your Arduino. Now, if you open your Arduino IDE and click on the little icon on the right top side with the magnifying glass, this opens this window. It's the serial console, and it will spy on the serial communication which comes from your Arduino. Now, you have here whatever comes from your Arduino, and this is probably the most important part, because you have to agree on the speed. If the speed is not in synchronization with your Arduino, then the text will be unreadable, garbled, or you just won't be able to read it. So whatever you use in your code as a speed, you must also set here. So our next example is called serial.helloworld.ino. So you can open that exercise file, and it's very simple. You will print hello world from this device, from the Arduino, back to your computer. So all what it does is just takes hello world and it sends out as digital data. Okay? So it's very simple. We are not even using loop. We are not even using loop. We're just using setup. So there are two things in setup: serial.begin and serial.printline. And serial begin sets the speed, serial print line sends hello world on to your Arduino. Okay? Yes?
What's the maximum speed of serial communication?
It depends on the chip, not on Arduino. The Arduino will say, the Arduino system will say it's 115,000 something odd bits, but actually at 16 megahertz you can go like 2 megabits. It's quite fast. You would have problem to print things time-wise.
Yeah, but that's the hardest
Yes. Yes. The chip supports it. Yes. So, for example, data collection, it's fine. It's okay for data collection. Quite fast. Millisecond rates. Yeah. Okay, so if you have done this, what you should see, I'll open the finished file. I'll cheat. Okay, so there is serial hello world. I open it, or you just typed it in yourself. I can hit upload right at this moment. So I can just hit upload, it will compile. Okay, it's compiling. It's compiling, it says how many bytes I've used. And it is important to remember, the Arduino will restart anytime you open the serial link. So you don't have to restart it manually, but what you see here is if you click the serial monitor, it says hello world. Okay, big deal, but it's actually a big deal. It's big deal because this chip is saying hello world. It's coming from your device, okay? And if you can reach the reset button inside, I'm not sure if I can reach it. Then if you reset it, it prints it again. If I reset it, it prints it again, okay? Because the setup program, your boot up program is running on the system. Okay, do we have hello world? If not, please, if you do not have the hello world program, please ask for help. Okay, ask for help. Every time you use the serial monitor, it's very important to set the correct baud rate. Unless you have the correct baud rate, it won't work. Okay, we will go and have a little bit of break soon, right? But not yet. Not yet. You have to endure one more little session here. And in here, we will talk about reading analog signals. Now, what do we have in our Flexi? We have a bunch of things which are working in an analog way. And of course, there's a plethora of excellent sensors which are sending analog signals, so just voltage changes. You have some of those devices on the screen. For example, this is a rain sensor. You can buy this on eBay for next to nothing. Okay, and connect it to your Arduino. So for example, rain sensor. This is an infrared distance sensor. This is a gas sensor. This is an acceleration sensor. This is a laser distance sensor, a microphone, temperature sensor. So all sorts of sensors actually do use analog signals to communicate with the microcontroller. But there's a question. You have a digital microcontroller. So how would you read a number that is analog? How would you need an analog voltage? And there is a bit of a philosophical problem here. Because whatever, yes, I'm sorry?
Those sensors?
A couple of euros. 1, 2, 3. Yeah. Yeah.
But they are from Arduino.
Arduino doesn't really make sensors. Arduino is an open source software and hardware. It means that right now you can access the web and download the blueprints for this thing and make it yourself. The only thing you shouldn't do is call it Arduino. You can call it Joduino, okay? That's fine. And the sensors can be found in many places. If you know Mauser, Farnell, whatever, or eBay, they're just a couple of really most of them are very, very cheap. I think every one of these here is probably under 2 euros, probably. Okay, 2 or 3 euros. Okay, so you can buy many. Now, let's get back to our philosophical problems. You have some sort of voltage range you want to read in. Let's say I want to read information or data from a sensor from 0 to 5 volts. But how many pieces, how many numbers are in that range? From 0 to 5. Infinitely many. And that's an issue. You have infinitely many numbers in the range of 0 to 5 volts. So you have to find a way to turn them to discrete digital information. And that needs a peripheral. And that peripheral is called an analog to digital converter. Not every microcontroller has such a peripheral, but your Arduino does, fortunately. So ADC stands for analog to digital converter. And you can see here, if you peek into your Flexi, it says analog in, and it says A0, A1, up to A5. So your Arduino Uno has 5 analog inputs. That means that out of the box, you can connect 5 analog voltage sources to these little pins. Now, just imagine what happens in the analog to digital converter. Imagine that you have 3 bits of digital information. You want to encode the voltage which you are detecting. Now, for 3 bits, what sorts of numbers you have? You have 0, 0, 0. And 0, 0, 0 will probably mean 0 volts. And let's say that the rail voltage of your microcontroller is 5 volts. So 5 volts will be 1, 1, 1. And everything in between, 0, 0, 1, 0, 1, 1, etc., will be one of these discrete levels. And this process is called quantization. So your ADC does quantization. It will divide your otherwise infinite precision to a given precision. So for example, if you would have a horribly bad 3-bit ADC, that would mean 2 on the third minus 1. So the biggest number is 7, and you have 8 different levels. You're dividing 0 to 5 to 8 levels, and that's your precision. There is nothing more. What is important to realize now is you're always losing precision. And the most important factor you have to look into when you're selecting an ADC is its resolution, its bit resolution. So the Arduino, fortunately, doesn't have a 3-bit ADC. It has a 10-bit ADC, which will divide the signal into 1024 various levels, which will mean about 5 millivolts of precision. I think that's quite decent, okay? So these things here, the ADC is a 10-bit ADC dividing your signal into 1024 various levels, having a resulting of 0.005 volts resolution. Now let's look at the Flexi itself. What does the Flexi have? Now the Flexi has this little knob in here. Okay, you have this little knob in here. This knob, how many of you are electrical engineers? None. Okay, how many of you are non-electronic engineers or electric engineers? Okay, quite a lot. All right, so this little knob, and then on the other side, I can actually see the other side inside, connects to a potentiometer or a pot. A pot or potentiometer is a variable resistor. They come in all shapes of sizes. They can be used, as in the Flexi, as user input. It's a really simple way of user input. But you can even measure angle with it. Think about it. It can be used to measure angle. Now, how does the pot work? You have some sort of resistive material. Okay, some sort of resistive material. And you can connect one end of that resistive material to 0 volt or ground. And here you would have 0 resistance. And on the other hand, you have the full voltage, 5 volts. And in between, you have a third output. This is called a Viper. And the position of the Viper is changing. Now, imagine what happens if you turn it all the way down. You have 0 resistance, and you have 0 voltage. Imagine what happens if you turn it to the other side. You have all the resistance which is in your circuit. So what you have in your Flexi is just this. You have a 3-terminal component. One end is connected to ground. The other end is connected to 5 volts. And in between, you have the moving Viper, So you can manufacture, you can make actually from 0 volts anywhere to 5 volts. And if you would connect the potentiometer to your Arduino, this is a mega, but it doesn't matter. This is how you would do it. If you take a potentiometer, you have a couple of potentiometers here and a couple of analog sensors. Okay, you can inspect these. There are lots of analog sensors and a couple of potentiometers. So this is how you would connect a potentiometer to your Arduino. The sides go to 5 volts and ground, and the Viper is your signal. And by this simple trick, you can detect the position of your knob, and you have a sort of a manual user input to your system. Now, let's try this. Let's try the ADC. There is an exercise file called Flexi ADC Levels. And it's, again, very, very simple. I have a little weird way of putting the brackets here, but that's just for one simple reason, so I can fit it in the presentation. So we can use this trick. Now, this trick is a very simple trick, which is in C. It's just a definition of a macro file. If I say define, so pound define ref A5, then when you're compiling, your compiler, actually the preprocessor, will change every single occurrence of ref to A5. This is just a way to do search and replace. Why am I using define like this? The reason why I'm using this is because I'm saving space. If I use a define preprocessor directive, then I'm not using a variable or anything else for defining where my analog voltage is located. So if you do define ref A5, then the preprocessor will will search for all occurrences of ref and replace it to A5. So what is A5? If you look into the Flexi, you will see that there is a wire coming out of A5, and that wire, mine is purple, I don't know what color is yours, it goes towards the pot. This is physically where the pot is connected. A5. There is nothing else. So now what we have here is, again, we are going to use the serial begin. Okay, serial begin. And in the loop, we are going to use the function to read an analog input. It says analog read. Analog read. And it just says where to read from. And we are going to store this number in an integer variable called ADC. An integer variable called ADC. Okay? So every time you call analog read, the microcontroller will read the voltage on A5, and it will output not a voltage. This is important. It won't output a voltage. It will output the level. Okay? So at 0 volt you have 0, at 5 volts you have 1023, and in between whatever you have. And then what we do is we do serial print line ADC, that's our number, and wait half a second. So upload this, type it up, upload this to the board. Yeah. So we have Flexi ADC levels. Okay. I'm uploading this to my Flexi, which I've disconnected, so it's not working. Okay, so what I have, if I open the serial monitor, I see numbers, okay? I see 676. And that's my voltage in the range from 0 to 1024. if you now turn around the knob, you can see how this is changing. Okay? So you have successfully read an analog sensor, one of the simplest types of analog sensor, which is a potentiometer. And now your user can communicate with the microcontroller. Okay, do we have that? Yeah? Okay, who has the pot reading? Okay, guys, we're going to have a short break and we should return around 11. Thank you for now and we'll see you later. You've seen that the ADC just tells you levels and numbers. What if you need the voltages? Of course you can measure the voltages. If you find the find the part where it says Flexi ADC voltages, then you see a little calculation here. So what are we doing here? How many volts is one level? If we go from 0 to 5 volts and we divide that by the number of levels, so 1024, that's how many levels we have. And if you multiply your number read by the ADC, then you get that number. So if you upload and run this little sketch, and then you open the serial link, just wait for it.
Why 5024 when we print the maximum value we get is 1023.
It should be 1023, yeah. So you have the voltages here, because that's the maximum voltage. Actually, no, it's good. At 5 volt, yeah, no, yeah.
When you change it to 23,
23, yeah, 23. Anyways, you're right. So what you have here is already the voltages. We can see the voltages here. Okay, it's just a simple calculation. I should put there 1023, and that's what you have here. You might want to ask, would it be better to recompute this in advance on paper and then use that number to spare one little operation on the microcontroller? Well, my answer is no. You can do it, it doesn't matter, but the compiler should be clever enough to do that for you in advance. So in the code which goes onto the microcontroller, you don't see 5 divided by 1023. You don't have that. It doesn't divide, your microcontroller doesn't divide that thing every time it runs. This is done in the compiler, and the compiler already beforehand tries to simplify those things. So in order to get voltages from the ADC levels, you compute the resolution and you multiply that number by the resolution. That's it. That's how you do it. The little trick, if you're a beginner in C, there are a couple of tricks. Notice that I'm not writing 5 and 1023. Instead I'm writing 5.0 and 1023.0. That's how my compiler knows that I'm using floating point numbers and not integers. And there is another trick in that little line. You see that float in the parentheses? This is called casting in C. And this solves my problem that here I have a floating point number. However, here I have an integer number. And this part, the casting, will tell my program to take the otherwise integer, which is coming from my ADC, as a float. Okay?
Could we directly define ADC as a float, because we define it as an int?
I'm not sure how the program would, the function would react. Probably it outputs an integer, so probably not. I can try, but yeah, because if this outputs an integer, then it would give me trouble about that. Okay, so if you have that voltage trick, I'll show you something else. So change the delay to 50 milliseconds. Okay, this is a very short milli. And now upload the code, the same code. We are reading voltages from the potentiometer. But the Arduino IDE of lately, besides the serial link, has another tool to spy on the serial communication, and this is called a serial plotter. So when you go to Tools and Serial Plotter, you get a little graphical interpretation of what's happening, and it's very small, you don't see much, but you can see 5 written there. So if I go change it, then I can plot what's happening. And of course, it's changing between 5 and 0. So I can spy on my communication what's happening here. It's a really simple tool. You cannot really set axes, or you cannot really set labels like you do in MATLAB. It's really simple, but it can be very, very useful to output things like this. Okay? So you have a little nice graphical representation of whatever is happening in your Arduino. It's the same thing, yes, serial. The only thing you need to take care of is you have a line ending. So you say serial print lemma. If you don't have that, it won't plot it. But the same exact way to plot it. Okay? Now, we have another analog sensor in our Flexi. And that analog sensor is actually the name of our little device. It's a flex sensor. This brown thing on the top is a flex sensor. It has 2 terminals, and the resistance of the sensor changes when you deform it. So you have a resistance change, okay? If your thing is flat, you have about 10 kilo ohms of nominal resistance, and it goes up to 25 kilo ohms if you deform it enough. If you deform it completely like this. Of course, with the fan, that will never happen. It won't turn it around onto the other side, so you can expect a little bit less of a range. Now, these things are used in robotics, used in assistive technology, medical technology, bio applications. So this sensor actually has an industrial use. Here we are trying to misuse it a bit for a little process control ways, but it's the same thing. Now, we said that the Arduino, the microcontroller, has digital inputs, digital outputs, right? It's clear. We can turn things on, turn things off. We have an analog input. We can read analog sensors. So that's taken care of. But we said that the flex sensor has a changing resistance. Now, how do you measure resistance if you cannot measure resistance with the device? Now, the simplest trick you can do, and this is pure electrical engineering, is you do a very simple circuit like this. This is called a voltage divider, and I'm not going to surprise you by saying that it divides voltage. Now, there is your incoming signal, the in and ground, and the out relation is given by this very little formula. Now, what we can do is we can use, instead of one of these resistors, we can use the flexi sensor, and that's how we can connect it to one of the analog ports in our system. Now, you might ask, which one of those 2 resistors should be the sensor and which one should be the fixed resistor? Or, for example, a potentiometer, so you can fine-tune it. Well, it depends. It depends what sort of sensor you have, and if you want the signal to be increased, the signal to be decreased. It's really up to you and up to the application, so there is no wrong or good answer. You can have the sensor to be the top one, you can have the sensor to be the bottom one. Now, in our case, if we use an incoming voltage, for example, 5 volts, and imagine that we have a flat sensor, which we said it's around 10 kilo ohms. Now, if we put 10 kilo ohms here, what will be the output voltage? Roughly. Take a guess. Half, yeah. If the 2 resistance values are exactly the same, it will be the half. So, if it's the half, our resistance can increase and decrease, and we can read this signal. We will have a level of 2.5 volts, and it can change up, it can change down. It doesn't actually matter that we don't measure the resistance of these things in ohms. We could recalculate it, but it doesn't matter. We just want to measure the change, and that is what is happening in the little flexi. Actually, I lied. This is not entirely what is happening in the flexi. This is the circuit. This is the circuit which is used in the flexi to connect your sensor to the microcontroller. And I'm going to touch on this subject just for those who haven't studied electrical engineering and just for your information. So this is the voltage divider part, which we talked about. Our colleague correctly said that if there are 10 kilo ohms, you get a 2.5 kilo ohm signal. But there's this little thing in the middle. This is called an operational amplifier. And operational amplifiers are incredibly useful and flexible things. But you could write books about operational amplifiers, and I'm pretty sure that someone has. However, we're using it in a very simple setup. In this setup, the operational amplifier is called a voltage follower. And in a voltage follower, it just takes whatever voltage it sees here and passes on to the microcontroller, 1-to-1. What does this mean? You can safely ignore it, because mathematically it doesn't change your voltage. What it does is it matches the impedance between your sensor and the Arduino. Now this is a little bit more complex issue. I cannot really take time to explain this, but just so you know, there is inside an operational amplifier. There's a little chip on the side. It has 8 leads. You can see it inside. Now that's the operational amplifier, and it's configured in a voltage follower mode in order to match the impedance, in other words, the dynamic resistance of your sensor and the Arduino. Now, you all know that measurement devices like oscilloscopes and signal probes and things like that have hypothetically very high or infinite resistances. And in case if you have a high resistance, then you don't need tricks like that. Now that's the theory. But in reality, the Arduino also has a very high resistance, mega ohms. However, when you're taking a sample in the ADC, this can drop. And this can drop a lot. And at that time, basically impedance matching starts to be a problem. Just so you know, what is that? Now, so you know, if you look at your little Arduino, there you have different wires, and A4, mine is red, A4 is connected to this little circuit, and it measures the flex sensor. So, your task now will be to open flex sensor that I know, and you can use the knowledge you already have to read the values. Now what we have here is again a little preprocessor definition. I'm just saying that change every occurrence of sensor to A4 at compilation time. I'm beginning a little bit faster serial communication, and what I have in the loop is I'm reading the analog sensor, and there is a function you haven't seen before. So this is, again, it's not a C standard function. It is an Arduino specific function. It's called map. And it linearly maps one number to another. So what it does, it takes the reading from the ADC, and it maps the original range of 0 to 1023 to 0 to 100. So we are trying to map ADC output to percentage. And then we output the serial data to the serial data and wait 100 milliseconds. Note that is very short time, and we are going to use the serial plotter to see what's happening with the flexi sensor. Okay? So type this down and upload to your system. You of course have the presentation. And the file is called flexi sensor Okay, so I just upload it. Okay, do we have it? Yes, we have it. And if you upload this and open the serial plotter, you have to set the speed to the same as we used. So these both. And now we have some sort of data. These are percentages, remember. And we do not have a calibrated sensor. So the sensor doesn't really know when it's flat. So what we have here, uncalibrated, is a number 53 or something, 53-ish. Now if you just hold the sensor in your hand and change it, you can see how beautifully it follows your hand. So our sensor is truly working. And as you can see, there is no big magic in this endeavor. It's just reading an analog signal inside. Okay, so try this out. Try to work with the sensor. Okay.
Sorry, and this point should be calibrated to 0, something like that. Adding enough.
Of course, your system is dumb. You're right. It would be better if it would say 0. How do you solve this? You program it. You have to solve all of this by yourself. Right now, we are just reading in the signal, and I'm outputting it from 0 to 1024. But of course, that can be lying, and you would need a calibration procedure to say this is 0. And actually, later, when we are going to use the library, which has been written by my colleague over there, it has a calibration procedure. But you can write one yourself. Okay? So it's not a problem. Right now, it doesn't matter that it doesn't say 0. It just matters that you see that you can try the sensor and use the sensor. Okay. So it doesn't matter that you start from 50 and it's not completely flat. Okay. If anyone has an issue, if anyone has a problem, please do not hesitate to ask our colleagues. That's why they are here. They will happily help. Okay? Does anyone know how to read the flex sensor? You guys? If you need help, please ask for it, okay? Guys, please, okay? Please help around. Yeah.
Permission denied when I uploaded to the comport.
Permission denied. I have. I'll call you guys. Eric, we'll solve that. Okay. Sometimes the COM port gets clogged. You need to close it and re-upload it. That mostly helps. Okay, you can go on working, and I quickly cover the third part. So how do we control the motor? If you look at your Flexi, you know that the input is coming from a fan. A fan, of course, is ending in a motor. So my first question is, can you just connect a motor or any sort of device with a high current need to a microcontroller? No, absolutely not. It would instantly destroy your microcontroller. So anything which draws a lot of current, like motors, have to be interfaced properly. I'm going to touch on that subject very quickly, but first, okay, let's say I interfaced my motor to my Arduino or to my microcontroller. If we have a function which says analog read, do you think there is a function analog write? Probably yes, and you would be right, but there is a catch. Analog write doesn't truly output analog voltages. So you cannot output 2.5 volts. You cannot output 3.3 volts. For this feature, you would need something which is called a digital to analog converter, DAC. And unfortunately, this one doesn't have one. So how can we still put out an analog voltage? Well, we can't. Instead of that, we use something which is called PWM, pulse width modulation. In pulse width modulation, we use a trick that we vary the time our signal is on. So if we want to create a 50% signal, which is 50% on and 50% off, then we simply alternate our signal between high and low. Okay, so this would be a pulse width modulation signal. Is this truly 2.5 volts? No, it's not. Would a motor or would an LED care that this is not 2.5 volts? No, it wouldn't. The motor would just run half the speed, and the LED would be roughly half as bright. So these devices wouldn't really care that you do not have a true analog signal. These devices would be quite happy with the PWM signal. Now your Arduinos do know how to output PWM signal. And in your Arduino, if you look into the box, you see these little waves. You can see those little waves there. And those waves mean that those pins are PWM compatible. So not every digital pin can do this. Only the ones which have the wave next to them. Okay? Yeah. So how do you use this? You have the analog write function. And again, it's important to know this is not a truly analog function. This is PWM. And the analog write function takes two things. The first argument is the pin you're using. And be sure that you pick a pin that is capable of using a PWM signal. And the second data is an 8-bit number that defines the duty cycle of your PWM signal. So what do we have at 0? What do we have at 0 value? At 0 value, we have 0 volts, right? Always off. Not too surprising. We said it's an 8-bit number, so what do we have at 255? 5 volts all the time. Anything in between is just switching on and off. So the speed of this switching is 1 to 2 kilohertz depending on the pin, so you wouldn't see it. If you connect this to an LED, then you won't be able to see it turning on and off. You will just see that it's not as bright as it should be. So this is an example. If you write analog write 255, you get a signal which is 100% on. If you get analog write 0, then you get a signal which is off all the time. Anything in between, let's say you want 50%, then you write about 50% of this number, 127, and then you get a nice alternating signal, very fast signal, on and off and on and off. And this way, if you hook your PWM signal to a proper amplification system, to an LED, an electromagnet, a motor, then the motor won't care that it's not a true analog signal. It will go slower than the full speed. Now, we don't actually have a motor. We do have a motor, but the motor is not just a motor, it's a fan. Now, this little fan is a very small and powerful fan. It needs 12 volts, and it takes about 4 watts of power. Again, as I said, you cannot just directly connect this to your Arduino. And this is exactly why we have the little adapter. Okay, this is the little adapter. It goes into this jack barrel. And in that case, you have two circuits. You have one circuit, which is your Arduino, and the other circuit, which is the power circuit. Now, just just to touch it. How can you connect anything which needs lots of power to the Arduino as a motor, such as this motor? Well, you use transistors. But transistors are a bit out of fashion today. So instead of transistors, we use a special type of transistor called a MOSFET. And a MOSFET is, again, just a special type of transistor for our system, which is voltage controlled and which switches very fast. So this MOSFET has 3 pins. It's just a transistor. Now you have one pin, which is the low voltage side. You can connect to this low voltage side to your Arduino pin. And the voltage on this low voltage side, controlling the so-called gate, that's why we have the G, the gate controls whatever is flowing between the drain and the source. And the drain and the source is called a channel. So by applying small currents, voltages here, you can control big currents flowing in here. It's just a gate, it's just a switch, essentially. Now what happens in your Flexi on the output side is this circuit. It's really simple. First of all, you have a low voltage side and you have a high voltage side. Now this resistance here is actually not a resistor. This is your load, which is the fan. And here you have a voltage source which doesn't come from the Arduino. This is your little wire from outside. And this is 12 volts, and this can handle lots of more juice than we otherwise could with the Arduino. Now what happens here is you apply a voltage to the gate, and the gate will switch on this little channel. Switch on, switch off, switch on, switch off. And this way you're not destroying your Arduino by hooking up 12 volts, 4 watts directly to the pin. Okay, so that is a way you can use for an electromagnet. That is a way you can use for an LED or a light or whatever. It can be even high voltage. It can be even 220 volts if you want, but the idea is the same. Now, just as a side note, what are these guys doing here? Well, the first one is called a gate resistor, and it protects the Arduino from the MOSFET drawing too much current and destroying the pin. The other one is a safety idea. When we disconnect it from the pin, what would happen if we wouldn't have this little resistor in here? The value would float. We wouldn't know what sort of signal goes into the gate. So it could hypothetically randomly turn on or randomly turn off. So we put there a small resistor which prevents this from happening. If you disconnect it from the pin, it will be always off. Now this is exactly the circuit which is going on inside your Flexi. If you take a look, you can see the MOSFET there. The MOSFET has this little heatsink. That's your circuit there. That's the MOSFET inside the power circuitry, and that's how you control the fan. Now, this exercise, you will control the fan speed of the Flexi in open loop. What does this mean? We will connect the reference directly to the fan and measure the output. Open loop, no control, okay? So you can see the listing here, okay? You can see the listing here. And we are not even plotting the output. We have two defines. One defines the reference, which is our little knob here. The other one is out. That's the PWM signal which goes to the MOSFET and from the MOSFET to the fan. So what this code does, if you have a look at it, it just sets the pin mode of the PW pin to output. We still have to set it to output. Then we read the analog reference as before. Then we map it from 0 to 1024 to 0 to 255. and then we write it to the output. We directly write, analog write to the output. So we are taking whatever information is on the knob, changing the range to a lower range, to 1024 to 255, and then we are outputting the same thing to the little fan. Now, if you do this, let's do this, then you can control the fan in open loop. So that's a flexi open loop. No, that's not flexi open loop, sorry. That's not flexi open loop. Flexi motor PWM. And I hear it, that's a nice sound because it's working. So, that's going to be annoying, right?
Can you set the PW frequency?
I'm sorry?
Possible to set the frequency of
It is possible to reset it to different values.
Can you go into the function?
You have to go around. Again, you're overthinking it. For most applications, you don't really need it. And it's on simplicity, but you can do it. You can do it.
It's annoying.
So you can test, you can see that there is a little... It's going to be difficult. Anyway, so there is a little dead zone in here. And then at full speed, you have the system.
Sorry for that.
No, no problem. Pani, Gabo, za tebou, za tebou, za tebou. Okay, guys, so if you're satisfied with your buzzing sound, then we'll move on. Oh, okay, yeah.
The high pitch sound you can hear, that's
the motor.
yes.
That's the drive frequency.
Actually, there is something like 480 hertz on the PWM signal.
That's what you hear.
This is called by the energizing the coils inside the fan, so you can literally hear it.
Yeah. Hear the noise. That could be measured. Yeah. Okay. So, I hope that you could control the fan, but now it's time to move on. So please turn down the volume for now. You can play around more later. So, first of all, you do have a library, and this is the first library you're going to need today. If you have the exercise files, there is the Flexi library. And you will need to either download this library from this address, is the GitHub of my colleague, or you can use the same exact library in a file called flexi.zip. Now, open your Arduino IDE. And you have tools. No. You have include library, and you have add a zip library, and find that file. Okay, this is how you can include a library to the Arduino IDE. So just find that zip using sketch, include library, add zip library. I can do it because I already have it inside. So it's sketch, include library, add zip. Sketch, include library, add zip. I'm sorry? Yes, it's in the base directory.
I am flexi.c.
Yes. Okay. So the library just makes everything what you did before a little simpler, because you access the pot, you access the flex sensor, and you control the motor from the library. But as you can see, you could have written those codes because you can already control these things. So first of all, if you want to use the library, you have to include a header file. Including a header file just means that the compiler, actually the preprocessor, will take that file and copy and paste it in the beginning of your own file with all the definitions of the code you will use later. You have to create an instance of this library, an object, by this piece of code. It says I am flexi, the pin which is connected to the fan, the sensor pin, and the pot pin. I hope this is right. Now, our colleague has mentioned that the little sensor doesn't read 0 when it's flat, and that's a problem. And that problem can be solved by software. And so we don't really waste our time writing that part of the software. There is a function for that, flexi.calibrate or calibrate. This is the function. You run this at the beginning of your code. What will happen is the motor will spin up, and it will do a series of tests. It lasts 6 seconds-ish, and then your numbers 0 and 100 will be nicely calibrated. There are 3 functions from this library which are very important for you. One is how to get the user reference, because that's our set point. That's our set points we want to track. And what's that? That's just reading the pot. You've done it, okay? So something like what you've done is this function, get user input pers. Pers means percentage. So your user input won't be voltage from 0.5. It won't be ADC levels from 0 to 1023. It will be percentage from 0 to 100. Okay? Then you have your output. And we control engineers like to call that Y. So our output Y can be read by this little line by saying get bend pers. And it will tell you the bending percentage, the bending value in persons from 0, flat, to bend, completely bent. And the final one is set fan speed pers. This will set the fan speed in persons. So 0 is off, 100 is full power, and anything in between is smaller. So you can already recognize some ideas from control engineering. We can call the pot as our reference and denote it with an R as a reference. We can call the output, the bending, as Y, and we can call the input as some sort of variable which is U. Now you can open Flexi Open Loop. And I'm going to, before you start to buzz with your little buzzers, I'm going to go through the code and tell you what's inside so you understand it. And then you can either make changes or do yourself. So the first line is pound include IAM flexi.age. What does this mean? This includes your library. And including is not a fancy thing. Your Arduino IDE, the preprocessor, just copies and pastes whatever is located in IAM flexi in that exact place. Okay, nothing fancy. Now we have 3 defines. These define the pins where the motor is connected, where the bending sensor is, and where the pot is. Okay? This line creates an instance for your library called Flexi. Okay, Flexi. Then you have your setup function. The setup function, as you know, is run only once. And we have to agree on the speed of the communication. And we run a calibration procedure here. This is the calibration procedure. It's nothing fancy. If you look inside the code, you'll understand it. Right. Now, we have a loop. What does the loop do? What does the fox say? Anyway, the loop reads the percentage of the reference, and we use a very, very complicated control algorithm saying that U is R. So we don't do any control. It's an open loop system. And then we send the fan speed to the fan. We read the percentage. And notice what I've done here. I print the reference. I print a space. And I print the output and wait 100 milliseconds. Now this is all we do. It's an open loop system. And if you do this, and now you can buzz, then you can see the open loop response of your system. So go flexi open loop. And open the serial plotter. Open the serial plotter. Okay, sometimes the ports tend to be busy because the same port is used for uploading as for reading. And you can see serial plotter, okay? I'll wait. Now, if you have this little thingy, remove it. Okay, this makes the response very non-linear. And we don't want that here. Okay, guys, please, there's someone who needs help. Now, what you have here is the open loop response. And as you can see, I've already set the reference to 25% and nothing is happening. See? So that's a problem. But if I raise it to 60, then it will respond. Okay? So what I want you to do in this example is make a step. Okay? Make a step manually like this. Make a step. And most of you, I guess, are control engineers. So try to determine the settling time and try to determine the gain. Okay, so you can do this actually from here. Settling time and gain. Settling time and gain. Okay? So, give me a quick estimate on the gain. Can you give me a quick estimate on the gain? One-ish, yeah, one. A little bit less, actually. Can you guess the time it takes to settle?
So it's already uploaded?
One. So a very crude guess is that the gain is around 1 of this system. This really looks first order-ish, okay? Any noise, anything you see here, the noise you see here is from the sensor. It's an imperfection. It's from the quantization. Okay, so you can safely ignore that. Otherwise, the response is truly linear. Now, we have guessed a gain of 1 and the time it takes to settle, so roughly this time is 1 second. So for a first order system, how much would be the time constant then? If the settling time is 1 second. 63%, 63.3, so about 0.63 is your time constant. Congratulations, you have a model. Okay. Can we go? Can we continue?
Sorry, can you say again my 66?
That's the time constant because of the logarithm. It's basic control science. The settling, the 63% of the settling time is the time constant of your first order system. It's from that exponential. If you do a logarithm, then it comes back.
So you have to go back to, okay.
Okay, so volume down. Volume down, please.
Is it there?
Yeah. Okay. Thank you. So we lose contact.
Okay, so if you do test, if you do a step test, even manually, what you can see is you can roughly determine the gain. Okay, so if I calculate that the input was, the required input was 42%, and instead I got 35%, then the gain I can say it's around 1, actually 1.8. The settling time, the time it settles, is about 1 second. So the 63% of that is your time constant. You already have a model. So that's a very crude model of the Flexi. So simple. Now, and I take a look at the time. I'll begin for 10 minutes and then we're going to continue. So, the most complicated thing you have to program yourself in a control system, if you're using a microcontroller, is sampling and timing. Of course, our digital control system is sampled. And we already said that the only way your microcontroller knows about time is this little oblong piece, which is the oscillator. And this is the time base. This is the base of everything. It's 16 megahertz. So it creates a pulse every 1/16 microseconds. Now, there is a couple of ways to measure time. First, let's talk about measuring time in an Arduino. You have two functions for that. One of them is millis, which tells you the number of milliseconds elapsed since the last start. And there is the function micros, and the function micros tells you the number of microseconds which have elapsed since the last time you rebooted your little system. So it's just a counter, it counts time. Now, not everything is perfect. Well, first of all, even if you're using micros, it's not a microsecond resolution, it's more close to 4 microseconds resolution. And there is another problem. You have to store these values somewhere, right? In your memory. And if you use a long integer, that's still a finite length number. So after time, millis and micros will overflow. It will count up, 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 but after a time there is no space to save your data. It will start all over again, overflowing. And for millis, if you use millis in your code, it will overflow in about 50 days. And if you use micros, micros will actually overflow in around 70 seconds. So it's not a great idea to use millis or micros for sampling. Now, how can you delay something? And you already know. You have delay, and you have delay microseconds. So you can do an even finer delay. You can do delay microseconds. Now, the issue with these functions is that they also derive themselves from the same sort of timing system as micros and millis. So that means that delay, it won't overflow, but it is similarly imprecise, so you have about a 4 microsecond leeway. And another problem with delay is the following. If you run delay, your microcontroller does nothing at all. It can't do anything else. It waits, but it can't do anything else. These types of functions are called blocking functions because they block the execution of your code. So again, it's not a great way to do sampling. Now, I guess all control engineers, you know what sampling is. We have to do repeated tasks at regular intervals. the regularity of those intervals is of essential importance. Without that, your control algorithm, your data collection, everything stands on its head. You won't get correct data, you won't get correct control. So it's very important that your sampling is kept, and it's kept at regular intervals. So first of all, you have to realize that in a feedback control application, you have a function which is run round and round, repeated at every sample. What you do there is you read your sensor, you write your actuator, you do your optimal control magic, you denote data. So these are repeated, and these have to come at very regular intervals. So let's call that function, you can call it anything you want, but let's choose to call it step. Step is actually something that MATLAB uses. When you compile a code from Simulink, it calls this step. This is a step function. So what you do in step, and this is just pseudocode, okay? You read the input, you read the sensor, you launch your control algorithm, whatever, but this step function must be launched at regular intervals. Now, we know that our algorithm and everything we do in closed loop control is located inside the step function. And I'm going to present you a couple of methods where you can see how horribly wrong sampling can go. So these are methods of bad sampling. Now, what if you would just put delay TS? What would that mean? Well, first of all, you do not take into account how long your algorithm and everything else takes. So you won't have a sampling time of TS seconds. You will have a sampling time of TS seconds plus whatever your algorithm takes. Bad idea. You say, okay, we can compensate for that. Let's say we measure the time our algorithm and whatever takes and compensate our sampling time with that. Well, not great. Not great because not every algorithm takes the same time. You know very well that optimal control can be quite unpredictable how long it takes. It can take a lot of time. It can take less time depending on the state. So a fixed compensation like this is again a bad idea. Never ever use these for sampling. These are bad ways to do it. Now a slightly better and decent way to do it would be this one. Okay, it looks a little bit complicated, but it's actually very simple. So this is our loop function, and if you don't put anything into loop, then it goes round and round and round and round as fast as it can. But now, at the beginning of our loop algorithm, I will ask one question. What is the time now? I'm just asking, what's the time? And I store that value in t. And then I have a little conditional if. And I ask, if I should run, if the time is the same as the next sample or slightly bigger, then I run my step. If not, then the loop will go around one more time and just ask, what is the time? Is it time to run my algorithm? If not, goes around. If yes, so you get the idea. Basically, we just ask and poll the time and go further. What is the issue with this? This is slightly more decent to run for sampling, but still not perfect. And the issue with this is that millis will overflow. It can be demonstrated. You cannot really tell what will happen. It will probably take really fast samples for a while. That's what happens. So this is, again, because millis will overflow is not very good, and it's not very perfect. Now, and I tell you, we will, I think, stop soon. Now, I'll tell you what's the good way to do sampling. Your microcontroller inside has a peripheral or a set of peripherals which are called timers and counters. Yet again, I'm not going to surprise you if I say that timers and counters are responsible for every counting and timing job you have on your Arduino. So timers and counters inside these peripherals, timers and counters, are responsible for you to work with delay macros, millis, micros, and even PW signal, everything where time is needed. So the code inside uses this. Now these peripherals are a part of your MCU, and you can access these. Now the timer itself is just, again, a memory address, this special fourth kind called a register. You can read and write a memory register like this. The Arduino Uno has 3 timers. It has, I think, 2 8-bit ones and 1 16-bit ones. Martin? Timers on the Uno, 2 8-bit and 1 16-bit ones. Yeah. I think 3, yeah. This one has 3 ones. The first one is 8-bit, the second one is 16-bit. What does this mean? An 8-bit timer is just a memory space which can count 0, 1, 2, blah, 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 up to 255. And then it overflows and starts it again. That's all it does. You can write this and you can read this. A 16-bit timer can count up to 0, 1, 2, 3, 65,000, whatever. Okay, so a 16-bit timer. Now, the timers can be configured in a variety of ways. You can say that you increase that number every time the crystal oscillates, right? So you do 0, the crystal oscillates, which is just 1/16 microseconds, and it goes to 1, and then another 1/16 microseconds elapses and goes to 2, etc., 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 and then after a while it overflows and does it again. Of course, this would be really fast counting. So these counters can have so-called pre-scalers. And pre-scalers just mean that you don't count every single oscillation of the oscillator. You just say, let's count every 64. And then what it happens is you start from 0, you wait 64 oscillations, and then it increases to 1. Do you get the idea how we can measure time like that? If I know the time between the increases of my counter, then I can measure time. And this is how time measuring works. Now the timers are really complex beasts and can be configured a million ways. They can count up, count down, etc. And I'm just showing you how you would manually use the timer, but we won't do that. So don't worry. It will look complicated. It is a bit complicated. I'm just showing to you what would you need to configure these timers. So, but before that, sorry. One thing and one excellent feature of these timers are that they can launch special little functions. So if a timer meets certain criteria, for example, when it overflows or when it reaches 200, for example, your little computer can launch a very special program or function you've written. This sort of function is called an interrupt. An interrupt function is called an interrupt because whenever an interrupt launches, your microprocessor will stop whatever it was doing and launch that program and then return to the original program. What does this mean? Let's think about it. How can I read in a button in a microcontroller? I can keep asking, is the button pushed? Is the button pushed? Is the button pushed? All the time, all the time, all the time. This is called polling. It's fine, but it's not perfect. The other way is I can say that an interrupt function should be launched every time the button is pushed. So if you push the button, a little special program interrupts your program flow and does whatever it needs to do. Such an interrupt function can be defined even for timers. When the time is up, do something. Now, these functions, the long way to say interrupt is an interrupt service routine. So if you say or see ISR, interrupt service routine. This is the same thing, a special little program that will interrupt the run of your code and do whatever it needs to do. Now, if the special program, the interrupt, is finished, then you return to the main program. And because everything else is left on the side, the interrupts have to be as simple as possible, as short as possible. You won't do long routines in interrupts. The interrupts usually just switch flags and switch things on and off really quickly and then return to the program, so you don't feel that you have to wait. Imagine using this polling technique with a button. So I want to know if the button is pushed. And what I do is I ask, is it pushed, is it pushed, is it pushed? But imagine that I have some sort of algorithm inside which takes 1 second. In that case, the user experience will be that sometimes your system registers the button push, sometimes not, because it's not there in your program. So that's why interrupts are very important. Now, this is the part I've mentioned, and I think then we can go to have a lunch then. So, this is the procedure to configure the timer 1. Remember, there is a timer 0. So this is timer 1, which is 16 bits in your little Arduino. This is what you would have to do if you would read the manual and do it like it should be. So first of all, if you mess with the interrupts, you want to turn off every other interrupt. So there is a code for disabling every other interrupt. Then, there are again special memory spaces which control the behavior of the timers and counters. Do you want to count up? Do you want to count down? Etc., etc. Now, these registers, these memory spaces, are called timer, counter, control, register for the timer 1A, etc., etc. You can find this in the manual for the chip. If you look up atmel 328 atmega datasheet, then you find all of this information there. Then you need to say, what I need to say, this little code which doesn't make much sense to most of you, but what I want to say is that I want to launch an interrupt each time my timer overflows. Okay, that's one way to do it. Each time my timer overflows, I want to launch an interrupt. Then what I can do, for example, is I compute how much time my sampling takes. So say I want 100 millisecond sampling time. I compute that with a given prescaler, how much time will the oscillator cycle to that, and preload that number to the counter. So I can write that register, and I can say that I'm starting from the number 25,000, I don't know how many, and then when I launch my microcontroller, it will start counting 25,000, 1, 2, 3, 4, up to the point when it overflows, but then nothing bad happens. I just launch an interrupt, and that's how I do sample. Of course, we said that we don't want to increase the timers, counters at every single count, because that would be really incredibly fast. So I can do something called the prescaler. I can say that I want to increase the count by every 8 step. And this is how you do it. And then what happens is, if I do this procedure, what you've seen before, and you do not need to understand it at this point, this is just illustration. If I do this at the beginning and configure my timer to do this, then every time the counter reloads, I can launch this program. Whatever I write into this program, this little function, this little function, will be launched at regular intervals. These intervals will be absolutely, strictly regular, and that's what you need for sampling in control engineering. Now, just one more minute and then we go for lunch. I spare you from configuring your timers and counters manually. You should, at one point, if you're planning to deal with microcontrollers, not just this, any one of them, at one point you should learn how to do it. But fortunately there is a library, because in the Arduino world there is a library for everything. And this library is called Timer1. It is included in your exercise files. It's called, I hope so, Timer1. And you should install this library to your Arduino the same way you did with the Flexi library. Okay, so that's where we stop and continue a bit later. Most of you are here. We said we're going to continue at 1:30, so we're going to do just that. So where have we stopped? We said that there's a couple of very bad ways to do sampling in a microcontroller. You can do like fixed delays, you can compensate the delays, but those are horrible things. Don't do that. What you should use are interrupts, but you also saw that configuring the interrupts manually, it's not that easy. You have to open the manual for the microchip and read about it. So this takes time. Of course, there are tutorials for it. But I have good news, because for the Arduino at least, there is a tutorial which, there is a library which takes care of this for you. And that library, and I really hope that you already have it installed by now, it's called the Timer1 library. Why is it called the Timer1 library? Because it will mess with the timer number 1 in your Arduino. Remember, in C, we don't do numbers from 1. We start from 0. So that's actually the second timer in your Arduino. And this is a 16-bit timer. Now, the Timer1 library takes care of this setup procedure entirely for you. So right now, please, go ahead, find the library file. It should be included with your examples. Okay, so here I have Timer1. This is the one. And installing the library to the IDE is the same procedure as before. So you go Sketch, Include Library, and Add Zip Library. Do we have the library? Hands up. We do have the library. Great. Then we can learn how to use the library. It's a really well thought out and well working library. Now, first of the things you have to do, similarly as with the Flexi library, you have to include the library. And again, just remember, including is just copying and pasting the functions into your code. So at the beginning, you include the libraries by saying timer1.h. Beware, the authors of this library were a bit inconsistent with naming, and sometimes they call it timer1 with a 1 number, and sometimes they use 1 as a word. So when you call the library, you use timer1 like this. Now, one thing is that the timer counts time in microseconds. So when you say I want 1 second sampling, that's 1,000,000 microseconds. If you put a constant in the beginning of your code, put it in a long integer, okay, a long integer type, store it in that. So let's say we want 100 millisecond sampling for our Flexi. That sounds reasonable. So what do I have to put in here for TS? That's 100 times 1,000. So the way you can turn on this library is you say timer1 dot initialize with the number in microseconds. Now, this little, very simple function takes care of everything I've just showed you before. So it selects a prescaler, blah, 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 everything. Okay? So just say, this is my sampling. This is my sampling. 100 milliseconds, 1 second, 10 seconds, whatever you need, timer1, initialize, and you're sampling. Now, the second line of code with this library you have to use is saying, what is the name of your ISR? What is the name of your very special interrupt function that you want to launch when the time comes? And when the time comes means at each sample. Now, this command goes as follows. It says timer1 dot attach interrupt, and here is a name which is a name of your function. It can be anything you choose. It can be doggies and kittens and whatever. I've chosen it to be step timer because it will be the function to time my algorithm steps. Okay, so include the library, initialize the library with the sampling, and attach the interrupt. Now, this is not everything. We've said that the interrupt interrupts everything what is going on in your microcontroller, throws everything away for a while, and then launches that function. So whenever my time comes, my sample comes, this way, my function, which has been attached, called step timer, you can call it something else, I just called it step timer, my step timer comes up. But we also said that because interrupts interrupt the work of your Arduino, this should be kept as simple as possible.
Can you pass arguments to interrupts?
Good idea. Good question. I think so. Yeah. I think so. You don't need any really arguments in this. Never really tried.
I'm guessing step enables a global variable.
Yeah. Yeah. I'm guessing. I'm guessing, but if I do an interrupt, I always just do flags on, flags off. So for this reason, to keep it very simple and short, what I do is I just use a global variable which says step enable. Step enable, again, my choice. It can be anything. My choice of variable, which will say that should the step be going on? Should I launch my measurement and control algorithms and data logging, etc.?
I see you're not locking in mutuses or something.
Sorry?
Like you're not locking in mutex or something. Do you have
No,
those
no.
conditions?
No, I haven't combined this. No mutexes here today. Not today.
Okay.
Not today. No fake multitasking today. No. There is no real-time operating system or anything else going on today. No mutexes, nothing like that. I'll show you. Yeah.
Why is it so important to keep this thing simple? Why not just?
You could hypothetically put everything. You could throw everything which is here. But remember that not only one interrupt function is possible. So imagine a power drill. Okay, imagine a power drill. Let's say you have buttons on the power drill, and usually these buttons are interrupts on their own. So imagine that the sample time comes, and you include everything you want to do in closed loop control in this one. But also imagine that you push a little button, and this little button will call another interrupt, and it will interrupt the interrupt. It will get crazy after time. What my colleague was referring to, mutex and real-time operating systems, these are really trying to ensure that your programs have priorities, blah, 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 blah. We don't use that here because, first of all, we don't have time to work with that. And second of all, we want proper control. We're not caring about the display refreshing properly and buttons and blah, blah, blah. That is also an important factor, but here right now, with this type of interrupt system, I'm just going to explain how to ensure that you have real-time sampling and it will be launched at the time you're really asking for. Yeah?
Is it possible to interrupt an interrupt?
Yes.
Yes?
Yes. Yes. Okay, so remember what happens. My counter will count. It will count up to 100 milliseconds. When the 100 millisecond comes, it will launch my little function which says step timer. Step timer does nothing. It just sets a global variable true. It says enable the step, launch the step, go with the step. Now, this is still not nothing. What I can do as a trick is I can put a loop function like this, okay? Loop checks all the time, all the time, all the time. And I just put there a conditional. If step enable is true, then launch the step. After my algorithm step, I do optimization, I go data collection, whatever. After that has been done, I reset the flag. I say, don't launch it again, okay? So, imagine what happens. we count, we count, we count, we count, we get to 100 milliseconds or whatever you set. An interrupt comes, and the interrupt only changes the value of the global variable. The global variable just says, enable step now. This goes as fast as it can evaluate an if conditional. It just says, is it time, is it time, is it time, is it time? When the interrupt sets that flag that yes, it is time, then the step function will be launched. But of course, after you have done everything you need to do, then you have to reset that flag again. You can say step enable false. By no means is this the only way to do sampling with interrupts on microcontrollers. This is a quite simple way, but actually, if you have ever used Simulink, and in Simulink you generated a code to hardware, this is exactly how Simulink does it.
Sorry, maybe you said it, but so these are not hard interrupts. So suppose the interrupt fires every 100 milliseconds, but your step takes 150 milliseconds, you'll just miss one.
Exactly. So that's another question I'm hoping to cover today. I might not cover it, but if my step takes 150 milliseconds, if my algorithm takes 150 milliseconds, and I want to sample 100 milliseconds, that's an issue. So you can put there very simple tricks, so at least you know that there is some sort of issue. But of course, it won't hardly interrupt the previous execution. It will just go to the next one. But that, of course, because we don't want to miss any steps, shouldn't happen. Yes?
Is there a way to put the CPU on a sleep before interrupt happens and wake on interrupt?
Oh, sure. Sure, but not. The AVR is not typically the typical processor you want to put to sleep. Maybe the 16-bit TIs and the ARM Cortex-A's are better. If you want to save a little bit of electricity, that's always good for battery-operated systems. So absolutely, you can do that. You can put the processor after the algorithm has run. You can put the processor to sleep and wait until the next interrupt, which will wake it up. Absolutely, you can do that. Okay, we will not cover that. Okay, so given that I can actually, yep.
I still have a question how interrupt is working. So when your time is done, so where is the time calculation here?
The time calculation is solved by this alone.
Okay.
The time calculation is going on in that little peripheral timer and counter inside.
Correct.
And it just adds up numbers in a register based on the increments of the oscillator. What I've showed you before the lunch break, that bit of a complicated setting thing, that was actually setting the timer. This just simplifies it for the Arduino. Okay? Right. Okay. So now let's try out this interrupt way of sampling on an LED. So you're going to flash an LED, but you're going to flash an LED based on interrupts and based on this sampling framework. So right now, I would suggest you just turn off the Flexi, part of the Flexi, and just use the Arduino. And before you go, I go over the program for you. So what we have here, we have an include here. It says include timer 1. This is our library for timing and nothing else. It's just timing. Then I need an unsigned long integer. It should be a constant, whatever. So I store my sampling time somewhere there. Then I create a global Boolean variable called step enable. Remember, this is the one which says, should I launch my step? Shouldn't I launch my step? So that's really easy. Now in the setup part, again, it's quite easy. We use the two very new functions you've learned about a while ago, which says timer 1 initialize, and it says sampling time, and I put it like this, times 1,000. So this is 1,000 milliseconds. This is times 1,000, so that would be 1 second, okay? 1 second timing. Then I attach an interrupt, and I call my interrupt step timer. I call my interrupt step timer. And then I set the LED, the little LED on the board as an output. Okay, so this is the setup part. And there's a couple more functions. So take a look at this very carefully. And I would skip over loop for now and go to step. So what does my step do? Now, I don't do any sort of closed loop control. What my step will do is kind of a dumb way to do it, but anyways, turn on the LED, wait 500 milliseconds, turn off the LED. You have to realize that normally this step would include your measurement, data collection, control, PID, whatever algorithm you're using. So that's really simple. This is my algorithm. I'm just turning a LED on and off. This one, the interrupt, is as you've seen. The interrupt just changes the value of the variable to true. Launch it. Go back to loop, and as you can see, loop is exactly the same I've showed you before. Loop goes round and round and round and round as fast as it can go, but at every cycle it checks. Should I launch the algorithm? No. Should I launch the algorithm? No. And if the time comes, the interrupt will change step enable to true. This runs, step runs, but after step runs, step enable is also changed to false, so it waits again. Back to that question of what happens if your algorithm takes too much time. Probably I won't have time to cover it, but there is a very simple trick. Again, if you use Simulink and you compile your code to hardware, this is what Simulink does, is in the step timer, it asks, when I launch the step timer, the step enable variable should be already false, right? Because it's finished in the previous step. So if the step enable variable is here true before I set it true, then I have a problem. And I can launch another function which either just stop the entire execution or say error or do whatever you want. But that time, the real-time, hard real-time constraint is violated. You have a problem. Now, try this, please, on your on your Arduino. You can open the file and see how it works. Yes. So you have a file called real-time constraint, and this file contains just whatever we set today. If you use the version, it's not real-time constraint, it's something else. Sampling test, yes. Sampling test. Please use the tutorial versions and fill it out yourself if you can. But if you do this, of course, you won't get anything very exciting going on. The only thing, you have a LED blinking again, but this operation is launching at 1 second exactly and always. And unlike in the case of millis or micros or any tricks like that, this will go on forever and ever, and it won't basically overflow and do unpredictable things after 50 days or after 70 minutes. Okay, so this is a more or less proper way to sample for your experiments and data collection if you are using a microcontroller. Again, there are millions of other ways of doing this, but if you put a block scheme together in Simulink and then translate it to Arduino or Raspberry Pi or even a PC, this is exactly how it does it. Okay? So do we have a blinking LED exactly at 1 second? Yep. Okay. I think this example is, I tell you what, when I start to talk to my students normally about interrupts and timers, that's probably the most boring lesson and lecture of all. However, there are a million tutorials on how to connect a gas sensor to sense your farts on your Arduino. However, there are 0 tutorials on how to do sampling properly. So that's why we're going into these details. And of course, this is not very pretty, but will help soon. All right, so we can sample now. And now that you can do proper timing, now that you can put things out of the serial console, you have a very, very powerful tool in your hand. And even if you're not planning to do closed loop control on the embedded system, just data collection for identification, this is already enough. And now, remember the test you did. These are my data. You could have different. So what I did, and you probably did as well, you tried a little step on the Flexi to see what happens. And you can read already a million things out of this simple test as a control engineer. First of all, we have an open loop stable system. Second of all, the behavior looks really just first order, nothing really fancy going on. Third thing, by comparing the input and output amplitude, you can calculate, even by looks alone, the gain of the system. I got a gain of 0.8. I've seen some people had even more gain, so it really depends on the Flexi you have, but it should be around 1-ish. Then the second thing you can do, you can just do a screenshot and compute the time it took for the signal to settle. Now, I guessed that my settling time to a flat steady state response was around 1 second. And if you go back to your linear continuous systems theory, then you should know that at 63.3%, you should have the time constant of your first order system. So my guess, based on that data, is that my time constant is 0.63 seconds-ish. Okay? So from that, you already have a very crude model of your system. And now, I mean, that's fine enough for the Flexi. Of course, it can be improved. But now I'm going to teach you how you can gather data to your computer from any sort of measurement. Okay? So this way, you can connect any sort of sensor to your Arduino, accelerometers, gas sensors, whatever, and correct data which is in real time. Now, there is one important thing. Even though you're sampling correctly on the Arduino, the data won't be pushed to the serial link, and by the serial link, the USB and your serial monitor in real time. What does that mean? Your data is sampled correctly, but it's not coming in real time. So for system identification, for plots, for everything you might need it, it's still correct. Okay? But it wouldn't be correct to assume that as soon as the sample occurs, the data comes to your computer. That's the only problem. Okay, so the way to do this is very simple. And we have to find some sort of structure. And that structure in your data has been around for decades already. You might know it as comma-separated values, or CSV. And the idea is very different, or delimited data. Very simple. Each row of your data is a time sample. Okay? So when you're finished with a time sample, you put a serial print line, go to the next line. Each column of your data is, of course, a data vector or a data point. And you can separate the columns, for example, by commas. If you just put comma between the columns, you get the format called comma-separated values. You can use tabs, you can use any other ways, but for example, if you use commas, then you can open your data in MATLAB, you can open your data in Excel, whatever, and it is real-time data. Now, this is just what I said. Now, for short experiments and for slow experiments, what you can do is you just sample correctly, send the data which is properly formatted, and send it to the serial monitor, copy, paste, and use it. Okay, it's no real science behind it. However, as I've told it, however, for faster experiments, so if you're sampling 10 milliseconds, each 10 milliseconds, it would be crazy to dump it into the serial monitor and save it. But fortunately, there is software. There's millions of free software which can do exactly the same thing as the Arduino serial monitor, that little window, and dump your data into a file. So you can have an experiment going on for 5 days and collect gigabytes of data, by that because it will save the data to a file. It won't be real time, but the sampling is real time, so you can feel free to use it wherever. Now, there is one important thing. The speed of the serial communication, of course, has an effect on how fast you can sample your system. And the speeds you can see in the drop-down menu in Arduino. If I go to the Arduino IDE, and if I open the serial monitor, you see that the largest number here is what? Oh, they've changed it. OK. So it's about 2 million baud. That's actually the hardware limit of the thing, of the AVR microcontroller in 16 megahertz. Pushing out data at 2 million baud is probably on the extreme, but I've used it. So it can be done. You shouldn't expect to sample even just pure measurements anything more than, with an Arduino, I would say millisecond. Okay, so if you need anything faster, then probably an Arduino is not a good idea. If you need a second sampling, 100 milliseconds or even 10 milliseconds, you're probably fine. You can use an Arduino for that. Now, as I told you, there are several sorts of software which do this job very excellently, and they are free. My favorite is CoolTerm. Do you have it installed? It's a really small free program. Okay. So there is RealTerm. There are millions of programs. You can do it in PuTTY, so it doesn't really matter. Now, each of these programs needs to know a couple of things. And first of all, where is your COM? Where's your port? And that's the same data you've set in the beginning in the Arduino IDE. So we had to find which serial port we are on. And as you can see, this is CoolTerm, by the way. If you don't have it, you can go to freeware.the-myers.org. And there is a Windows, Linux, and Mac version of this software. And if you go to receive, then you can do all sorts of fun things. And this is my favorite. You can say capture file location. So you can directly dump your data into a file, which you can open later. And this data, when it's saved, can be later opened in MATLAB without any reason. And you can do all your usual magic in MATLAB on the data itself. Now, we'll have a little data collection experiment, which will be used in system identification. Our test signal for system identification will be a series of on and off changes, which will last a couple of seconds. And we will collect this data and then read it into MATLAB. So it is an open loop experiment, but you won't control it by hand. Okay, we will determine it beforehand that it should turn on and off, on and off, on and off. And what we want to dump to the output, to the serial link, is just the output and the input to the system. Now, this is our code. It's a little long. So what I would suggest is you either follow along in the presentation or just open the code. And let's see what we do. There should be no new parts. We've talked about anything. This is a combination of the concepts which we've done before. Okay? So there is absolutely nothing new. Now, we need two libraries, one for timing, one for communicating with the Flexi. We have a couple of defines here which just say which pin, which physical pin I have the pots and the flex sensor and the motor connected to. The next thing is the initialization of the Flexi library, which we've done before. And then there is a bunch of variables, and half of this should be actually constant, but I was lazy to do that. So there you go. There's a couple of things we want to measure. First of all, we have sample time. We want 0.1 seconds, so that's 100 milliseconds. Then I put here a number which counts the samples. Okay, 1, 2, 3, 4, the samples in my experiment. This is my experiment duration. This is the duration of one of the cycles. So I want 50 seconds on, 50 seconds off. Okay. This is a step enable flag, you've seen this. And these are my inputs because I don't want to go 0 to 100%. I want to see a more typical range of operation for my system, so I go from 25% to 60. If this doesn't work for you, just change it around. And I initialize the input with the low, so we start with the low input. Okay, so these are just numbers, most of them are constants actually, which we use later in the program. Okay, so the setup is very easy. We initialize serial, we calibrate the flexi, we initialize the timer, we attach an interrupt. Okay, nothing too surprising here, that's all has been covered before. Now the loop, you may recognize the loop. My loop function is nothing else than before. It is just asking, should I start, should I start, should I start, should I start? And if it should start, then it just launches the function step. Now, I jump to the back. My step timer, again, is the previous one. If the interrupt occurs, I just change a flag. Nothing new. And here is, and I think in the exercise files, here are parts you can fill in. Here is my little step function. It might not be perfect, but it works reasonably. So what does it happen? First of all, I set the output. Then I read the input. Now this part of the code, you don't need to worry about too much. It's just a logical exercise. You can do it as homework. But it just switches between up and down values, okay? It just switches between two extremes. This is nothing too interesting. And note this part. This part is very interesting for you. Note how I formatted my output. I print k, which is the sample number. Then I print a comma. Then I print u, which is the input to the system. Then I print a comma. Then I print y, which is the reading from the flex sensor, but I end the line. Get it? So we have a line where we have three pieces of data divided by a comma. That's comma separated values. Now, this little else part is just ensures that after my experiment is done, because this says if my time of the experiment is still going on, then it just turns off my experiment. Is that okay? Is that clear? Nothing new here. Okay, so let's try this. Let's do a sampling test, and if you have the little CoolTerm software, the Myers, then you can try to mess around with that and try to read in the data into that and save it into a file. Okay, so I repeat it with you. And I go, so this is flexistep.ino. Flexistep.ino. I open it. I won't type it in, I just upload it. And now remember, every time you connect to the Arduino via serial, it will restart. And we will not need the serial monitor inside the IDE. So now I have it turned on. It's not on, but it doesn't matter. And what I will do is I open CoolTerm, if I find it. Yep, it's here. So this is the little CoolTerm software. And what I can do is I set my CoolTerm up. I said options. I have COM18. Okay, this is my COM port, COM18. And here, check this. Here, I said capture file location. So I can capture into a file, which in my disk will be C CoolTerm win. So what I do is I say OK, and I can do connection, capture to text file, and start. I can do start, And here are my captures. I can say tempo capture. Save it. And I can connect now. I'm connecting now. And I can hear that it has restarted. The calibration procedure is on, and actually it says 0 bytes. And now we have the data, and what's the issue? I made a mistake. Can you tell me what's the issue? Baud rate. Exactly, the baud rate is wrong. So I go again. Options. I do 115/200. I do capture to text file. Start. Tempo new. And I can go connect. Again, restart. And there's my data. There is my data flowing in. This is the sample. This is the input. And this is the output. See, the data is flowing in. My experiment is completely automated. Yep.
Can you specify the location of the file?
It asks if you go connection. If you go connection, capture to text file, it will ask.
Yeah, and then you just go to the and do automatically save.
Yeah, it will save online. It will save. Okay. So I can stop. Yep. Please, can you ask these guys, okay? Now I'm looking at the mess I have on my C drive and trying to find the file.
How do you stop it?
There's a stop. It's here. It stops automatically, by the way, but you can say capture to text file stop. So here are the captures. And here is the tempo new. So if I open this, what I have is a beautiful file, which is a comma delimited file. Okay. I hope you have the file already. It says ASC, okay, something ASC. If you don't, if you got stuck, if you don't, then in the same directory, there's this file called flexistep1asc. You can use this. Now, if you have MATLAB, I can show you how to read this data in. So if you start MATLAB, if you go to the directory, okay, I just go to the directory here. I just use the one I've and what was the name of the experiment? Flexi. Yeah, I'm just. What was the experiment? FlexiStep, yeah, FlexiStep. And I see the ASC file. That's the same file I got from the CoolTerm. And here in MATLAB, you have. I can. Okay, like this is okay. I don't want to change the resolution because then the presentation is bad. Okay, so if you go to your MATLAB, you have a part here called import data. You have import data, and if I select this, I get a graphical user interface where all the data is in one single column. This is not good. So what I do in this case is I can say what are the column delimiters? This is important. What are the column delimiters? And we know what are the column delimiters? They are commas. So I can go comma. And as soon as I go comma, MATLAB will realize that these are columns. And I can even rename these. I can say that this is time, this is input, and this is output. It's here, import data. You can rename right here, okay? You can rename right here. And if you're satisfied with this, you can import it as column vectors, as matrices, structures, whatever you want. I've chosen column vectors. And if I click import selection, then you can see that I have 3 pretty vectors here, and I can do whatever I want in MATLAB. So I can plot, for example, the output, and you will have your experiment in MATLAB. You can do system identification, you can do plotting, you can do data analysis, you can do whatever the hell you want to do. Okay, so import data, you file the data, you find the data, you choose the proper delimiter as comma, you say okay, and you can import all of these, import selection. That's all you need to do. Of course, there's a command line version. So if you do a lot of experiments like this, you can automate it in the command line. That's not an issue. So, if you have your data in MATLAB, then there is a little M file in there called plot results. It does nothing else, just plot the results. Not too surprising. So I hope you do have some sort of plot. We can go plot results, which looks like this. Okay, so this is the input output experiment we did, a little experiment on the Flexi. Do we have the data? Data? What's the issue? Try to talk to the guys. They're sitting there and getting bored. Gabriel, can you help these guys? Okay, if you get stuck, then you can use my data. Okay, you can just use my data.
Which was the extension of the data file?
I'm sorry?
What was the extension of the data file besides? What was the extension besides text file?
ASC.
SC.
ASC. It can be whatever you want. It doesn't care. Eric, please, can you try to help around?
So the ASC is not coming out of the cool
term, but the ASC is arbitrary. It can be TXT, it can be CSV, it can be whatever one. It's just a text file, yes.
But which is minimum sampling time? Then if we reduce it, or how can I know when I get some problem or?
I'm afraid I can't cover this because of a lack of time. The trick is just to let you know that it's not coping with it anymore.
Okay.
So the way to check this, in your interrupt, you say...
Is what you explained before.
Yeah.
But if I don't do that, and now I reduce the sampling time, and it's not able
you
to...
You can't reduce it to infinity. I mean, up to 10 milliseconds, it's reasonable to expect that it will work. Below that, you can be afraid that something is not good. I'm just speaking out of my experiment.
If it doesn't have any instruction, you just continue to the next.
Yeah, it would leave out samples. But that's why it's a good idea to leave there the time, like K, 1, 2, 3, 4, and then you know. You can even interpolate in MATLAB. Yes?
I found it somehow. That's not a problem now. So I find this split STC45, but that is my input and output.
Javier had similar problems. Did you turn on the pulse?
Okay. Can I get a moment of attention? A very common issue is, especially in Windows, that two programs cannot use the serial port at once. So if you have Arduino IDE open with the serial monitor or serial plotter, then it's likely that CoolTerm won't work. So what I would do in this case is close the Arduino IDE completely and just use the CoolTerm. Okay? Two programs cannot use the serial link at once.
Sorry.
Yep.
Can you just show again how to set CoolTerm for
Yes. Yes, so I'm showing again how to set CoolTerm to receive data. So I open CoolTerm. I go connection and options. I need to set two things. I need to set the port, COM18, and I need to set the speed. I can go OK. Now, it doesn't matter, because I'm telling you why. Because if you go capture to text file, and if you say start, then it will ask. Now it will ask, and I can say this is OK or something else is OK. I hit enter, and I can say connect. At this time I say connect, and it says, shoot, sorry. And now it says capturing 0 bytes, but it says capturing 0 bytes because the calibration procedure is going on, and it will send the data only after that. Okay? Let's just ignore that I've turned it off.
So import data with text file. Sorry. Can you show your CoolTerm settings because it doesn't in the receive.
There was no setting beside the baud rate and.
You have trouble with Mac or? Robin, you have trouble with Mac?
Oh, that's a Mac. We didn't expect it to work. Essentially.
Can you show what's on the receive?
Which one? Receive? Okay, I'm afraid I would love to wait for everyone to finish, but I need to move on. So if you don't have a model, then you can use my measurement, okay? In the upcoming time. So how many of you actually has some data to work with? Not excellent, but good enough. Okay, good enough. You can still repeat this at home. Okay. So, let's move on to something which is not completely connected to the embedded part. So I will just fly through it really quickly. And this is creating your model. Okay, so let's create a model from this. So let's see if this is good. So what we can do is we can assume, you can turn the flexes down now, all right? So what we can assume is that we can reasonably well use use a first order model reasonably well. And what you can do now is you can import the data. If you have your own data, work with that. If you have my data, then use that into MATLAB workspace. And if you have the system identification toolbox in MATLAB, then you can run this function called process like process estimate. And P1 just means a first order system. So if you have your data, your input output data in the system data, and if you run process P1, then you can identify your data. So this is an M file, and it will only work if you have the MATLAB system identification toolbox. Okay, what does this M file do? First, for me, it loads the data. If you have your own data, please use that. Okay, use your own data if you have that. With ID that data, I create a data object. The data object has an output, has an input, and has a sampling time. If I run this ID data, I will have everything stored in the variable data. Now, what I did is I just looked at the data and I didn't like the beginning, so I picked a nice clean portion. You can do this on your own, or you can just leave it out. It's up to you. This picking of data is basically just the same matrix notation you're used to in MATLAB. And then I run the process model estimate function on my data, and I'm saying that I expect a model as a first order transfer function. And whatever I get in model, that will be my model. And there is another trick. You can use compare data and model. So you can match your data with your model. Okay, so this is not really embedded stuff. It's control engineering stuff, system identification. But let's try to do that.
How did you create this data?
I've just saved it in the MATLAB workspace. So if you have Y and U already in your workspace, then you can just use that, and the load data can be left out. I've just saved whatever I imported.
Only Y and U.
Y and U should be the measurement what you imported. TS, you know TS because you've set it in your Arduino. Okay, so this is Flexi process model, and I have my data saved, but you can use your old data if it's saved, or you can use Y and U, which has been imported from the CoolTerm. And if I run this, it says, first of all, it says that I have a data file, and wow, here is the system identification from my data. Sorry about that. Well, first of all, my rough crude test, just by my eyes, my system identification works very well, because actually, based on the data, it says that my gain for my experiment, for my Flexi, was 0.83. And my time constant is 0.65. See, I've guessed 0.8 and 0.63, so that's not bad. Our crude model was good, but you guys can have a different model because every Flexi is a bit different. Now, when you run this compare, if you run this compare part, then you get a plot which should looks like this. Now, the gray is my data. And the blue is my first order model, this guy. So you can see, not great, decent, I would say workable model. Of course, you can go into nonlinearities and whatever, but this, for our cases, it's a quiet, decent model in our working range. So we do have a model. Everything is percentage in and out. So we do have a model, and our model is this one. Okay, so we have a model. Did anyone manage to get a process model? Okay, so you have your very own process model. That's great news. You can work with that process model. If you managed to take a wild guess based on the measurement, use that as your model, okay? It's not an issue. Hush, I didn't want to do that. Okay, so I don't want to spend way too much time on this part. It's system identification, it's not embedded part. You should already know it, okay? But what we have to do now is to create a state space model, okay? We are talking about the course on embedded optimal control MPC, so most of these representations, I'm guessing, is in state space form. So again, nothing embedded here, it's just control theory. Now you need to remake your transfer function model into a state space form. So if you have a transfer function like this, and this is your gain, and this is your time constant, of course, you can rewrite that as a differential equation. This is my differential equation. Here is my time constant, times the derivative of output, plus output equals 0.83 input. Okay, this is just a differential equation for my first order model. Now, we are quite lucky because we have a first order model, so it's not really an issue to make this into a state space representation. So what you do is you can say that your only state, only single state what you have is the output. So x equals y. So if you do x equals y and you move the largest differentiation to the left side and the rest to the right side, then you divide by the time constant, then you get a nice first order state space equation. This is still state space, it's just a first order state space equation. So if you do have your very own model, then you can do this very basic manipulation. Again, just control theory, nothing embedded here. And now, of course, what we identified here, or by your eye, is a continuous model. And we want to do discrete control, discrete time control. So again, we go back to MATLAB, and we can say that if the sampling is 0.1, and my gain, I noted with k, whatever, my gain is 0.83, my time constant is 0.65, then I can, based on that manipulation you saw in the previous slide, I can say that my matrix, which is of course a scalar, now is -1/t. My b, which should be in general matrix, is k/t. And c is 1 because we say that our state is equal to our output, and we do not have a D matrix. Now, I'm assuming you are very familiar with this in MATLAB. So in MATLAB, you can create a state space system by saying SS for state space with the matrices or scalars in this part, A, B, C, D. And you can use C2D to discretize that. And then here, maybe you can compare the step response. Whatever you get for SysD, that's your discrete system. That's your discrete state space system, just a first order system that you will be using next to actually finally do some closed loop control. So if I run this, or if you've been, I hope, following along, don't look at my license number, please. Okay, that's not it. So I can go flexi state space. Then I can run this to discretize. And my discretized matrices are here. It's not really a big job. But you have to do it. You have to discretize your matrices, and then you can maybe compare the step response of your continuous and discrete system just to be sure. All right. Now, do we have a state space representation in the discrete time of those of you who used your own model? Anyone? Okay. Anyone following along? Okay. If not, you can use the one I've used. Okay, it's close enough for your flexi. So you can just assume that my flexi is really the same as your flexi. Okay. Now in this part we are a little behind schedule, a lot behind schedule. Anyways, there are some parts which I have to skip. We will do a closed loop LQ control on the flexi. Finally, some closed loop control. And there are some ideas about execution timing measurement and real-time constraint violations, and even Kalman filters that I've included in the presentation, and there are also examples for it. If you're interested, please feel free to look at them, but unfortunately, due to the time constraints we have today, I cannot cover those parts. But don't worry, they are not necessarily needed later. Okay, so what we are going to do later doesn't really need it. Now, what we are going to do now is to design a very simple LQ controller for the flexi. There is, in the library of the flexi, there is a PID controller. You can play around with this, but the reason why today we would rather design an LQ controller is because we want to talk about optimal control, hopefully MPC, and we would need a state space representation anyway, so let's do that. Now, in the flexi, you want to check some sort of reference. You have a set point, and the set point is set by the knob. So we have to remove any sort of tracking errors. Now, one way to remove tracking errors is to augment our state space representation by an integrator state. And this integrator state is really simple. I just say that my integrator state is my previous integrator state or current integrator state plus the error. What is the error? The error is the difference between my output y and between my set point r. That is my error, and I'm just going to add this up, sum this up. So this is my first order state space equation for summing up my errors. It's essentially an integrator. Now if you look at that and you move one step backwards in time, then you can write the same thing. So if you know the integrator's state at the previous step and the error in the previous step, then you get the current integrator. Now, you can, of course, use the Z operator, which is actually just a one-step delay, to see how does this look like as a transfer function. So we can replace the delay operators with a Z on the minus first, on the power -1. And if you redo a little transfer function, then you can see that this is actually nothing else but forward Euler integration, our little steps. Now, this is probably quite irrelevant for the embedded implementation, but let's go back at our integrator. So what is our integrator? Our integrator is the next integrator is the current integrator plus the error. And the error is the difference between the set point, my knob, and the output, which is the position of the sensor. Now, of course, y, we know y is the output, and we know that that's matrix, or this time scalar h times x. And we know that our matrix is a scalar, is just a 1, and x is the same thing as y. So we can use this to augment our state space system. So what we do here now is we combine the integrator with the model we had before. So let's say we start with the integrator. You can start with the model too. It doesn't really matter. And let's look at this. So the integrator state is the integrator state in the previous step minus hxk, this is this, plus 0u, we don't have u there, we don't have the input there, plus rk, this is the reference. So that's the first equation in our augmented state space system. The second one is just a state space system. We have a first order one, but this would work, of course, with larger ones. The next state is the dynamic matrix times state now plus the input matrix times the input and 0 times the reference. So this is our augmented state space system we made for our little flexi. And if you call this, for example, f tilde and g tilde, then you have a new, let's say, augmented sort of state. Augmented state is the augmented state matrix times the augmented state. You get the idea. Now, if you would like to imagine how our control system, our LQ control system for the flexi will work, this is the diagram. So you have the plant, and you design an LQ gain, but not just for the dynamics of the system, but for the entire augmented state space system. And then you're using your little augmented state, and this one is just an integrator. We just add up the errors. This is our reference, and the difference between the reference and the output is our error, and the integrator accumulates the error. Here is the integrator state, here is the dynamic state, and here is the augmented state, which we will use to multiply our LQ feedback with. So what's our job? Our job is to create this augmented matrix with our very own model, and I hope you have your very own models, or not. Compute an LQ controller and use it on the flexi and see if we can do a nice closed loop LQ control of our flexi system. So let's do that. So I would suggest some penalties here. You can try run your very own. I would say the state penalties should be a 1-1 diagonal matrix, an identity matrix. And for the states, you can use a penalty of 5. Okay, that worked for me. It's likely to work for you as well. So we're not here to do control theory. So you can jump to MATLAB and compute the LQ gain by DLQR, the discrete LQR. So if you open in MATLAB flexi LQR.m, then you have my discrete matrices, which are not matrices but scalars again, for the flexi system. If you have your own, then use your own. I perform the augmentation here. I just say what the penalty is, and I run the LQR, and I get an LQ gain. So try to do that. Try to run that in MATLAB, and hopefully you can have an LQ gain designed by your very own model of the flexi. So if I just do that, I'm not even going to go to MATLAB right now. If I do that, then I get, for these numbers, this LQ gain. Okay, this is the LQ gain for my model. If you have a different model, these are the discrete matrices, scalars. This is the discrete version, then this is your gain. Okay? We don't need this. Now, let's try this. The only thing you should have at the moment is an LQ gain which was designed by your model. If not, just use the one I have. It's likely to work. Now, I will not list the entire file. The file which you will see now is exactly the same as you have used for the system identification example. What does that mean? You have the input-output library of the flexi. We have sampling by the timer 1 library, and we have some sort of printing. There is nothing else there. You already know this. So what I'm going to list, but of course feel free to open the files. What I'm going to list here soon will be only the step function, only the algorithm function, okay? So, about the integrator. First of all, the integrator is to be reused at each step. Your step function has to remember it. There are ways to do it. The laziest way is to make it a global variable, okay? Now, we do not need a state observer, not really, because the output, we said, is the same as state, and we don't care about the noise. We should, but let's ditch the state observer. So first of all, we can integrate our error that we can just sum up, and we can measure the output, which is the state, so we do not need an observer, okay? Now there's one thing to realize. The integrator is related to the previous error. If you use the current error, you're changing up your integrator a bit, and instead of the forward Euler, you get a backward Euler. It will probably work, but it's not the same actually. Okay, so we are using the previous error. Now, the code actually for our integrator is this. It's nothing else. It's xi is the previous xi, the error. And what is the error? The error is the reference minus the output. Why am I computing this afterwards? Why am I computing the error only after I do the integrator? This is exactly what I said. If I do it before, I have a backward Euler. If I have it afterwards, it's a forward Euler formulation. It's just a slight change in your model. Okay, so do it afterwards. And here's the step function. As I said, you can open now flexi lq int exp. So that's flexi lq integrator experiment. You can look at the file, which is the same, really the same as the previous ones, except for the step function. So let's have a quick look at the step function. This is a bit of an ugly and dirty way to store my variables and initialize them in the function, but that's okay. It's educational. Right, so I have a gain. This is a floating point number. And why don't I say double? Does anyone know why don't I say double here? I could use double. The issue is that unfortunately none of the microcontrollers in the AVR family use double precision. So even if you use double precision in your C code, it will be turned to single. This is an important point to make, and an important point to make because it can cause some numerical instabilities if you have really fancy, advanced, and complicated algorithms. Now, this is my gain, and I store my gain as an array. I put here some sort of upper and lower limits. I have an integrator and an error. The static modifier just means that inside my function, I'm making a global variable. Static is needed, so my function, when it's started the next time, doesn't forget about the integrator or the error. Now, we can go on. We can write the actuator, read the sensor, and get the user input. Okay? So this is nothing really surprising. Read actuator, read user input, output. Now here is the rest of the step function. Here is my integrator. I'm just summing up my error. I'm computing the current error. And I just do the LQ control law, LQ tracking control law. And what do? I got, for the augmented system, I got a gain row vector because it assumes I have two states. And I have two states. And the first of that state is the integrator state. And the second of that state is the output, which is my measured output. Okay? So I can do in one line, this is minus Ka, the first element, I mean the zeroth element, the integrator state, plus Ka, y, which is the second state.
Then to declare before the dimension of u?
The dimension of what?
Of u, like the output u?
U was declared before somewhere globally. Just look at the code. There must be U somewhere, because I'm just showing the step part. Now, look at this. Look at this line. It's again another Arduino language specific line. Constraint is just a constraint of some value U. If U is any higher than UH, then it will be kept at UH. If it's lower than UL, then it's cut to UL. I don't want to put anything else into my hardware in order not to damage it. So as a safety precaution, I cut the U's this way. Now, I didn't list the printout. I made another function. At this function, we'll just do the serial printing. If you want, open the file and do printout. Now, if you, yes?
So, for example, this constraint, I mean, I'm not very aware of this language, for example, or whatever.
It's just
it's a box constraint. So I would have written equals condition, which would, I guess, more mean so efficient. So where can I get this kind of listing of everything, like constraint or whatever, all kind of functions that they use it?
It's part of the Arduino language. It's really simple.
Yeah, just sure, but like there should be like set of them, correct? Or it's like
there's a set of Arduino specific. Yeah.
So is there a listing somewhere?
Yeah, absolutely. You can look it up. You can look Arduino language reference. But it's a C function. You can program this yourself. Yeah, exactly. You can say just if it's higher, that's the same thing, okay? Now, just try to fill this. And we have flexi LQ int exp. Okay, and this is the same function as before, so I can upload it. And your controller will not be perfect because it will not know about the dead zone from 0 to 20 or 0 to 30, but it's likely that after that it's quite nice. So if I open my tools and serial monitor, no, not serial monitor, serial plotter, then I can try my LQ tracking controller. And here you can see the green value is input, I think. The blue is the reference, and red is what we get. So you can see we got pretty good tracking control. These little spikes are not your fault. They are the fault of the design of the output reading. They can be improved on, but for now don't really care about that. So there you have a tracking LQ controller with your flexi. The green is input. So red is the output.
Push with your finger.
Yeah, it tries. At least it's not that effective, but at least you can hear that it's trying. It's trying really hard. It's not perfect. It's what we got in a day. Kedy máme pauzu? Teraz? O tretej?
No.
Okay, if you haven't used your own model, of course, then the response might be a little bit worse, but to be honest, with this simple system, it's not likely to make a whole big lot of difference. So what you can do, what you can try, is you can blow onto the flexi to see if it gets it back to the track, okay? You can try this, or you can push it very gently with your hand and listen how the fan tries to compensate for it. Guys, do not use this. It makes the response non-linear on purpose. It makes control harder. Remove this. This is just to make the response non-linear and hard to control. So do not use this.
Yes,